Chapter 3, Unit 3, Algorithms and Programming. 3.1 Variables and Assignments. What is a variable, really? Let's start with an analogy that's going to stick with you all the way to exam day. Imagine you have a whiteboard in your kitchen, and on it you write the word groceries with an arrow pointing to a list: milk, eggs, bread. That label, groceries, is your variable. The list itself is the value. And the beautiful thing about a whiteboard is that you can erase the list and write something completely different tomorrow. The label stays the same, but the data it refers to can change. That's the core idea behind a variable in computer science. It's a named storage location in a program's memory that holds a value, and that value can be updated, replaced, or used in calculations throughout your code. The College Board defines a variable precisely as an abstraction inside a program that can hold a value. Notice the word abstraction. That's key, AP vocabulary. A variable lets programmers work with data without worrying about exactly where in the computer's memory that data lives. You give the data a meaningful name, and from that point on, you refer to it by that name. Think of it like how you say call mom instead of reciting a 10-digit phone number every time. The name is the abstraction. The phone number is the underlying value. How assignment works, and how it's different from math. Here's where students trip up constantly on the AP exam, so let's get this absolutely clear. In mathematics, the equal sign means two things are the same. 5 equals 5, always, forever. In programming, the assignment operator is fundamentally different. When you see something like score plus 10, that is not an equation claiming both sides are equal right now. It's an instruction. It says take whatever value is currently stored in the variable called score, add 10 to it, and then store that new value back into score. The arrow, that left-pointing arrow, is the College Board's notation for assignment throughout the AP CSP exam, and you need to be completely comfortable reading it. Other courses or languages might use an equal sign for assignment, but on your AP exam, you will see, and you need to know it means store this value in this variable. So if score currently holds the value 45, then after executing score plus 10, score now holds 55. The old value of 45 is gone, overwritten. This is one of the most common MCQ traps. A question will walk you through 3 or 4 assignment statements, and then ask what the final value of a variable is. Students who treat like a math equals sign get completely turned around. Students who treat each line as a sequential instruction, read the current value, perform the operation, store the result, get it right every time. Types of values variables can hold. On the AP exam, you'll work with a few fundamental types of values. You have numbers, both integers like 7 and -3, and numbers with decimal points like 3.14. You have strings, which are sequences of characters. Think of a string as text wrapped in quotation marks, like hello or AP exam. And you have Boolean values, which can only be true or false. That Boolean type becomes enormously important when you get to conditionals and logical operators in the next few sections, so file it away now. You don't need to declare a type when you create a variable in AP pseudocode. The language College Board uses on the exam is loosely typed, meaning you can assign a number to a variable and later assign a string to the same variable without the program complaining. In practice, you wouldn't do this in most real programming contexts, but understanding this flexibility is important, so you don't waste time on the exam wondering whether a variable assignment is legal. Tracing through variable assignments, the exam's favorite game. The most reliable way to see whether you truly understand variable assignment is through tracing, manually stepping through code line by line and tracking the value of each variable. College Board loves these questions. They'll give you a sequence of assignments and ask for the final state. Let me walk you through an example that captures every trap they like to set. Suppose you're given this sequence, x3, then y7, then xy, then yx. What are the values of x and y at the end? A student who skims this might say x is 7 and y is 3, as if the two variables swapped, but trace it carefully. After line 1, x is 3. After line 2, y is 7. After line 3, x gets the current value of y, so x is now 7. Then line 4, y gets the current value of x, but x is already 7, so y becomes 7 as well. Both variables end up holding 7. The original value of x, which was 3, has been permanently lost. This is an absolute classic MCQ trap. If the question intended a true swap, there would need to be a temporary variable to hold one value while the other gets copied. Something like temp x, then x, y, then y temp. Watch for this pattern. It shows up in both multiple choice and free response. Naming variables and why it matters conceptually. While the AP exam won't test you on syntax rules for naming variables the way a Java or Python course would, it will test your understanding that a good variable name should be meaningful and descriptive. A variable named x tells you nothing. A variable named total score, student age, or isGover communicates intent immediately. College Board emphasizes this in the context of program readability and maintainability, two concepts that show up in the course's broader discussion of good programming practices. When you see FRQ questions that ask you to write pseudocode, using clear, descriptive variable names is a low-effort way to demonstrate understanding and can earn rubric points related to code clarity. Connections to the rest of the course. Variables are the atomic unit of nearly everything you'll do in AP CSP. When you reach conditionals in section 3.5, every if statement will compare the value of a variable to something. When you reach loops in 3.6 and 3.7, you'll use variables as counters that increment with each iteration. When you tackle lists in 3.8, you'll use variables to store index positions and traverse data. And in the Explore Performance task and the Create Performance task, understanding how data is stored, named, and manipulated is foundational to explaining your program's functionality. Variables also connect directly to Unit 2's discussion of data. After all, a variable is how a running program represents and manipulates data in real time. Without a firm grip on variables and assignment, everything that builds on top of them becomes shaky. With variables firmly in your toolbox, you're ready to move into the world of expressions and operations, where those stored values start interacting with each other in meaningful, powerful ways. 3.2 Data Abstraction, Lists and List Operations. What is data abstraction, really? Let's start with a question. Imagine you walk into a coffee shop and order the usual. The barista knows exactly what you mean: medium oat milk latte, 2 pumps of vanilla light ice. You didn't have to specify every detail. That single phrase, the usual, is a form of abstraction. It bundles a complex set of instructions into one simple, reusable label. Data abstraction works exactly the same way in computer science. Instead of tracking every individual piece of information separately, we group related data under a single name and work with that group as one unit. In AP Computer Science Principles, data abstraction is formally defined as a way of managing complexity by giving a collection of data a name and using that name to interact with the data without needing to know how it's stored internally. The College Board wants you to understand that abstraction reduces complexity and allows programmers to focus on what data does rather than how it's physically organized in memory. That distinction, what versus how, is critical for both multiple choice and free response questions. Lists, your primary tool for data abstraction. The main data structure the AP exam focuses on is the list. A list is an ordered sequence of elements. Think of it like a numbered grocery list. Item 1 is milk, item 2 is eggs, item 3 is bread. The order matters. The items are all grouped under one name, your grocery list, and you can refer to any item by its position. That position is called an index. Here's the part that trips up students every single year. The AP exam uses one-based indexing. That means the first element in a list is at index 1, not index 0 like in Java, Python, or most real programming languages. When you see a list called scores with 5 elements in an AP pseudocode problem, scores 1 is the first element and scores 5 is the last. If a question shows you a list with 4 items and asks what scores 5 returns, the answer involves an error. That index doesn't exist. This is one of the most reliable MCQ traps on the exam, so tattoo it on your brain. Index starts at 1 in AP pseudocode. The 4 core list operations you must know. The College Board tests you on 4 fundamental list operations, and you need to know each one precisely. First, you need to know how to access an element. You do this using bracket notation with the index, as in milli eth3. Second, you need to know how to assign a value to a position like milli s2 99, which replaces whatever was at index 2 with the value 99. Third is appending, which uses the command append, mylist, value, to add a new element to the end of the list, making it one item longer. Fourth is inserting, using insert, mylist, I, value, to place a new element at position I and shift everything at that index and beyond one position to the right. There are also remove and length operations. Remite mylist. I deletes the element at index I and shifts everything after it one position to the left, so the list gets shorter. Length, mylist, returns the total number of elements currently in the list. You'll use length constantly when writing loops to traverse a list, because a well-written traversal goes from index 1 to length, mylist, handling any list size without hard-coding numbers. Traversing lists with loops. Speaking of loops, traversing a list means visiting every element, typically to read, modify, or process each one. The standard pattern in AP pseudocode uses a for each loop. For each item in mylist processes every element from first to last without you ever touching an index manually. Alternatively, you might use a counter-based loop from 1 to length mylist when you need the index itself during processing, for example when comparing adjacent elements or modifying values in place. A common exam scenario shows you a list traversal and asks you to predict the final state of the list or the output of a displayed value. When you work through these, track the list's contents step by step. Draw a small box for each element and update it as the code runs. Watch especially for loops that use append or insert inside them. Those change the length mid-loop, which can cause unexpected behavior if the loop's stopping condition is based on lengths evaluated once versus re-evaluated each iteration. Why lists enable abstraction? Here's the conceptual piece the College Board loves to test in free response. Lists allow programs to manage data without knowing in advance how many items there will be. Instead of creating individual variables, score 1, score 2, score 3, all the way to score 100, you create one list called scores and write code that works on any number of scores. This is the power of abstraction. Your code becomes flexible, reusable, and readable. If you later need to handle 200 scores, you change the data, not the program logic. This connects directly to Unit 2 on binary and data representation, because every element in a list is itself data that gets stored and processed, and it connects forward to Unit 4 and Unit 5, where you'll write procedures named reusable code blocks that take lists as parameters. The idea of passing a whole list to a procedure rather than passing each element individually is itself an act of abstraction, and it's a pattern you'll see on FRQ questions asking you to write or complete a procedure. Edge cases and boundaries that appear on MCQs beyond the indexing trap. Watch for these boundary situations. What happens when you call append on an empty list? It works fine. The list goes from having 0 elements to having 1, and length goes from 0 to 1. What if you insert at position 1? Everything shifts right, and the new element becomes the first item. What if you remove the only element from a list? The list becomes empty. Length returns 0, and any subsequent access attempt on that list would produce an error. The exam might show a loop that removes elements one by one and ask whether the program crashes. The answer depends on whether the loop's condition correctly checks that the list still has elements before trying to access or remove one. Connecting it all together. One last thing to keep sharp. The College Board may describe a list using natural language and ask you to represent it in pseudocode, or show you pseudocode and ask you to describe what the list represents. This translation skill, moving between abstract description and concrete implementation, is exactly what data abstraction is about. If you can explain why a list is more flexible than separate variables, describe what each operation does to the list's size and content, and correctly apply one-based indexing in every problem, you're in excellent shape for this topic. With lists now firmly in your toolkit, you're ready to move into the real engine of programming, algorithms, where you'll start using these lists to search, sort, and solve problems in systematic, step-by-step ways. 3.3 Mathematical Expressions. What is a mathematical expression in code? Let's start with something you already know. When you write 3 plus 4 on a piece of paper, that's a mathematical expression, a combination of values and operations that evaluates down to a single result. In programming, it works almost exactly the same way, except now a computer is doing the arithmetic, and the result gets stored somewhere or used to make a decision. That shift from pencil and paper math to computer-executed math is what this section is all about. The College Board defines a mathematical expression in the context of programming as a combination of numbers, variables, and arithmetic operators that produces a value when evaluated. That phrase, produces a value, is important. Every expression evaluates to something. The expression a plus b doesn't just sit there, it collapses into a number. Keep that idea in your head because it connects directly to how variables work in Unit 3.1 and how conditions work in Unit 3.5. The 4 operators you must know. The AP exam tests you on 4 arithmetic operators, and 3 of them are completely familiar: addition, plus, subtraction, minus, and multiplication arts. Notice that multiplication uses an asterisk, not the times symbol you're used to from math class. That's because computers need a symbol that can't be confused with a variable name. The 4th operator is where students start to stumble, and that's integer division, or more precisely, the combination of division and what the AP exam pseudocode calls the MOD operation. In the College Board's reference language, the pseudocode used on your exam, division between integers results in the integer quotient, meaning the decimal part is simply dropped. So, 7 divided by 2 doesn't give you 3.5, it gives you 3. Think of it like splitting a pizza. If you have 7 slices and 2 people, each person gets 3 slices, and that leftover slice just sits there awkwardly. Integer division throws that awkward slice away. Then there's mod, which does the opposite, it keeps only the remainder. 7 mod 2 gives you 1 because 7 divided by 2 leaves a remainder of 1. A beautiful real-world example. If you want to know whether a number is even or odd, you check number MOD2. If the result is 0, it's even. If it's 1, it's odd. You'll see MOD come up constantly on the exam, especially in loops and in problems involving patterns or cycles, like figuring out what day of the week it is after a certain number of days have passed. Order of operations. Yes, this still matters. Here's something students sometimes forget. Programming follows the same order of operations you learned in algebra. Parentheses first, then multiplication and division, including MOD, then addition and subtraction, moving left to right when operators have equal precedence. The College Board will absolutely give you a complex expression and ask what value it evaluates to, and if you forget that mod has the same precedence as multiplication and division, you'll get the wrong answer. Walk through this example the way the exam wants you to. 3 plus 4 times 2 mod 3. Multiplication first. 4 times 2 is 8. Now mod 8 mod 3 is 2 because 8 divided by 3 is 2 with a remainder of 2. Finally, addition. 3 plus 2 is 5. The answer is 5. If a student jumped to adding 3 plus 4 first, they'd get a completely different and wrong answer of 2. This is one of the most common traps on multiple choice questions. Slow down, follow PEMDAS, and treat mod exactly like multiplication in the order of precedence. Variables and assignment, the expression in action. Mathematical expressions become powerful when you combine them with variables. An assignment statement takes an expression, evaluates it, and stores the result in a variable in AP pseudocode that looks like x 3 plus 4, which assigns the value 7 to x. The arrow is the College Board's assignment operator, and it always flows left. The expression on the right gets evaluated first, and then the result gets stored in the variable on the left. Here's a classic exam trap. What happens with xxx plus 1? A student who hasn't internalized how assignment works might say, that's impossible, x can't equal x plus 1, but in programming, the right side is evaluated first using the current value of x, and then that new value is stored back into x. If x was 5, it's now 6. This is called incrementing a variable, and it shows up constantly in loop. Recognizing this pattern, using a variable's current value to compute its new value, is fundamental to understanding algorithms in Unit 3 and beyond. Expressions inside algorithms and procedures. Mathematical expressions don't live in isolation on the AP exam. They appear inside conditionals, inside loops, and as parts of procedure calls. When you see a loop that says repeat 10 times, the 10 is an expression. When you see a conditional that checks if score mod 2 equals 0, the left side of that equality check is an expression. Understanding that expressions are the building blocks woven throughout every algorithm helps you read code more fluently during the exam. This topic connects tightly to Unit 3.12, which covers calling procedures and using return values. A procedure can return a mathematical expression's result, and then that return value becomes part of a larger expression. Picture a function called double n that returns n times 2. When you write x double 3 plus 1, the procedure call evaluates to 6, and then the full expression becomes 6 plus 1, which stores 7 in x. Breaking complex expressions apart piece by piece, evaluating inner parts first is exactly the skill the exam tests. Boundary cases and edge conditions. 2 edge cases show up repeatedly on multiple choice questions. First, division by 0. If a program attempts to divide by 0 or use 0 as a divisor in a mod operation, the result is undefined and typically causes an error. The exam may present code and ask whether it contains a bug, and division by 0 in a mathematical expression is a classic answer choice. Second, watch for expressions involving negative numbers with MOD. The College Board's pseudocode is designed to avoid ambiguity here, but in real programming languages, MOD with negative numbers can behave unexpectedly. If the exam gives you a mod problem, assume both operands are positive unless stated otherwise. Connecting it all. The reason mathematical expressions matter isn't just arithmetic. It's that they're the engine underneath every algorithm. Every time a program counts, calculates, compares, or transforms data, a mathematical expression is doing the heavy lifting. Master the operators, respect the order of operations, internalize how assignment uses expressions to update variables, and you'll find that reading and tracing code becomes dramatically more intuitive. With expressions firmly in your toolkit, you're perfectly positioned to move into the next section, where we'll see how programs use these computed values to ask questions and make decisions, which is the heart of conditional statements. 3.4 Strings. What is a string, really? Let's start with the most fundamental question. What exactly is a string? In the world of AP Computer Science principles, a string is a sequence of characters. That's it at its core, but don't let the simplicity fool you because strings show up everywhere on this exam, and the College Board has some very specific ways of talking about them that you need to know cold. Think of a string like a necklace of beads. Each bead is a character, a letter, a digit, a space, a punctuation mark, even an emoji if you want to get creative. The necklace as a whole is your string. The order of those beads matters enormously because cat and tack are made of the exact same characters but are completely different strings. Position is everything. In the College Board's pseudocode, which is the standardized language used on the AP exam, strings are written with double quotes around them, so hello is a string, 42 is a string even though it looks like a number, and 2 quote marks with nothing between them is an empty string, which is a valid string with a length of 0. That empty string edge case shows up in multiple choice questions more often than you'd think, so tuck that away. String operations. The AP exam tests. Now here's where we need to get precise, because the College Board tests specific string operations and uses specific names for them. You need to know these operations, what they do, and critically how they handle edge cases. The first operation to know is len, which returns the number of characters in a string. If your string is hello, then len hello returns 5. If your string is hello world, that space in the middle counts as a character, so len hello world returns 11. This is a classic trap on the MCQ section. Students forget that spaces and punctuation are characters too. Every single character between those quote marks counts. The second major operation is concat, which stands for concatenation. Concatenation means joining 2 strings together end to end. Concat hello world gives you hello world. Think of it like snapping 2 Lego pieces together. The first string's tail connects directly to the second string's head, with nothing added in between unless you explicitly include it. A very common MCQ trap here involves forgetting to include a space. Concat hello world gives you hello world, no space, and that missing space can completely change the meaning of your output. The third operation is substring, and this one requires your careful attention because it has multiple parameters and a specific indexing convention that trips students up constantly. Substring takes a string, a starting position, and a length, and it returns the portion of the string you specified. Here's the critical detail. In the College Board's pseudocode, strings are 1-indexed, meaning the first character is at position 1, not position 0. This is different from many real programming languages like Python or Java that start counting at 0, and switching between those mental models is one of the most common sources of errors. So if you have the string computer and you call substring computer 24, you're asking for 4 characters starting at position 2. Position 1 is C, position 2 is O, so you grab O, M, P, U, and your result is OMPU. Practice a few of these by hand before your exam, because the College Board loves testing this with just enough complexity to make you second-guess yourself. Variables, concatenation, and dynamic strings. Strings become far more powerful when you combine them with variables, and this is where the connection to the broader programming concepts in Unit 3 really clicks into place. You can store a string in a variable just like you store a number. If you write name Alex, then name holds the string Alex. You can then use Concat to build new strings dynamically. Concat hello, name would produce hello Alex. This matters enormously for the AP exam's Create Performance task, where you'll need to demonstrate meaningful use of programming constructs. Using strings stored in variables, concatenated dynamically based on user input or program logic, shows the kind of abstraction and programming sophistication the rubric rewards. Think of a program that generates personalized messages, welcome back, username, that's string manipulation doing real work in the world. Strings are not numbers, a critical distinction. Here's a misconception that costs students easy points. A string of digits is not the same as a number. 42 and 42 are fundamentally different things to a computer. The string 42 is 2 characters, the character 4 followed by the character 2. The number 42 is an integer you can do arithmetic with. You cannot add 10 to 42 and get 52. You'd be performing concatenation, not addition, and potentially get an error or 4210 depending on the language. The College Board tests this distinction. If you see a variable that holds 42 in quotes, treat it as a string. If the exam shows arithmetic being performed on it, look for whether there's a type conversion happening. When the pseudocode keeps the quotes, it's a string, full stop. Traversing strings with iteration. Strings connect directly to the iteration concepts you'll study in sections 3.7 and 3.8, because you can loop through a string character by character. Imagine processing each character in a user's password to check whether it contains a number, or scanning a piece of text to count how many times a certain letter appears. You'd use a loop from position 1 to length string, extracting substring, my string, I1 at each step, that gives you 1 character at a time. This pattern, the loop combined with len and substring, is a favorite on the FRQ section, and understanding it shows you've truly internalized how strings work structurally. Edge cases and exam traps to remember. Let me give you a rapid-fire list of the edge cases you absolutely must know. An empty string has length 0, and calling substring on it should be treated as an error condition. Asking for a substring that goes beyond the length of the string, for example, asking for 10 characters starting at position 5 in a 7-character string, is also an error. Spaces count as characters in the LEN. Strings are case-sensitive. Hello and hello are different strings. Concatenating a string with an empty string returns the original string unchanged. Concat hello is still hello. On the multiple choice section, when you see a string question, slow down and trace through the operations step by step, keeping the 1-based indexing front of mind. Draw it out if you need to, write the string, number each character starting at 1, and then apply the operation manually. That 30-second investment has saved many a 5 on this exam. With strings now firmly in your toolkit, you're ready to start connecting them to the logical and conditional structures coming up next. Because once you can store and manipulate text, you'll want to make decisions based on what that text contains. 3.5 Boolean expressions. What is a Boolean expression? Let's start with something you already understand intuitively. Imagine you're deciding whether to go to a party tonight. You might think, is it on a Friday or Saturday? Or is my homework done and do I have a ride? Those little mental tests, the ones that end in a yes or a no, are Boolean expressions. Named after the 19th century mathematician George Boole, a Boolean expression is any expression that evaluates to exactly one of 2 values, true or false. That's it. No maybe. No sort of. Just true or false. On the AP exam, College Board calls these values Boolean values, and the data type that holds them is called a Boolean, sometimes written as bool in some languages, though the AP pseudocode just uses the words true and false directly. This section is foundational. Boolean expressions are the engine behind every decision a program makes. When you get to conditionals in section 3.6, loops in section 3.7, and even algorithm efficiency later in the course, you'll find Boolean expressions sitting quietly underneath all of it. Master them now, and those later topics will feel almost effortless. Relational operators, making comparisons. The most basic Boolean expressions use relational operators to compare 2 values. College Board's AP pseudocode uses a specific set of these, and you need to know them cold. The equals comparison is written as EX meth, not like in Python or Java. On AP pseudocode, it's just a single equals sign used for comparison. You also have not equal for less than, for greater than, less than or equal to, and for less than or equal to, and for greater than or equal to. Think of relational operators as a scale at a doctor's office. You put two values on either side, and the scale tells you the relationship: heavier, lighter, or equal. So the expression score greater than 90 is asking the question, is the score greater than 90? If score holds the value 95, the whole expression evaluates to true. If it holds 85, it evaluates to false. Simple, concrete, clean. A classic AP trap here involves the difference between if for assignment and equal E for comparison. In the pseudocode, x5 assigns the value 5 to x, while x equals 5 in a Boolean context is a comparison. Read context carefully. If you're inside a condition statement, it's a comparison. Students who come from Python or Java backgrounds sometimes second-guess this because it looks like the assignment operator in those languages. Trust the AP pseudocode convention. Logical operators and, or, not. Here's where Boolean expressions get powerful. You can combine multiple Boolean expressions using three logical operators, and, or, and not. These work exactly the way they do in everyday speech mostly. And requires both conditions to be true for the whole expression to be true. Think of it like a bouncer checking two IDs at once. You need a valid ID and you need to be on the guest list. Both requirements must pass. So, score greater than 90, and attendance equals true, only evaluates to true if both conditions hold. If even one is false, the whole thing is false. Or requires at least one condition to be true. This is where students stumble, because in everyday English, or sometimes implies exclusivity like, do you want coffee or tea, implying you pick one, but in programming and on the AP exam, or is inclusive. If either condition is true, or both are true, the expression evaluates to true. It only fails when both are false. Picture a hotel keycard door. It opens if you have a room key, or if the staff override is active. Both working at once, still opens. Not simply flips the Boolean value of whatever follows it. Not true becomes false, and not false becomes true. It's the logical equivalent of saying the opposite of. So not score greater than 90 is equivalent to asking, is the score not greater than 90, which is the same as score not greater than 90, which is the same as score a less than or equal to 90. That equivalence comes up on the exam frequently. Truth tables, your visual tool. For the AP exam, you need to be able to construct and interpret truth tables, which are charts showing every possible combination of inputs and the resulting output. For a two-variable expression, you have four possible combinations: both true, first true, and second false, first false and second true, and both false. Drawing a truth table is straightforward. List all combinations systematically, then evaluate the expression for each row. For and, the only row that gives true is when both inputs are true. For or, the only row that gives false is when both inputs are false. Memorize those two anchor points, and you can reconstruct any truth table under pressure. De Morgan's laws, the high-value concept. One of the most frequently tested edge cases on the AP exam involves De Morgan's laws, which describe how not distributes across and or. Here are the two rules stated precisely. Not A and B is equivalent to not A or not B, and not A or not B, and not A or B is equivalent to not A and not B. Notice that when you push the not inside the parentheses, the and flips to or, and the or flips to and. A vivid way to remember this. Imagine you're saying, I do not want coffee and donuts. That means you don't want coffee, or you don't want donuts if either one is missing. Your demand is satisfied. The and becomes an or when the not moves in. College Board loves to present two expressions and ask whether they're equivalent. De Morgan's laws are almost always involved in those questions. Common MCQ traps and scoring pitfalls. Beyond De Morgan's, watch for these traps. First, nested not operators, not x is greater than 5, just gives you back x is greater than 5. Double negation cancels out. Second, operator precedence, not is evaluated first, then and, then or, similar to how multiplication comes before addition. When in doubt, use parentheses to clarify. Third, on free response questions, writing a condition incorrectly by even one operator, say, instead of I greater than or equal, costs you that scoring point. Precision matters. Reread the problem to confirm whether boundary values should be included or excluded. Connections across the course. Boolean expressions don't live in isolation. They are the condition inside every if statement you'll write in section 3.6. They control whether loops continue in section 3.7, and they appear in the searching and sorting algorithms you'll analyze in section 3.11. When you study the explore task and written responses later, being able to explain why a condition is written a certain way demonstrates the deeper understanding that earns full credit. Boolean logic is also the mathematical foundation of how physical computers work at the hardware level. Those true-false values correspond directly to the ones and zeros of binary, which connects back to Unit 2 on data representation. With Boolean expressions firmly in your toolkit, you're perfectly set up for the next step, using them to direct the flow of your programs through conditional statements. 3.6 Conditionals. What is a conditional, really? Let's start with something you already know how to do perfectly. Make decisions. Every single morning, without even thinking about it, you run a little mental program. If it's raining, grab an umbrella. Otherwise, leave it at home. That's a conditional statement. And it turns out computers think in almost exactly the same way. The difference is that computers need you to spell out every single branch of that decision tree with absolute precision. No guessing, no reading between the lines. Just clear, logical instructions. A conditional statement, the way College Board defines it, is a statement that uses a Boolean condition, something that evaluates to either true or false to determine which block of code gets executed. The College Board refers to these as selection statements, and that word is intentional. Your program is selecting which path to take. You'll see the term selection used heavily in the AP exam, so make sure that word is locked in. The if statement, the foundation of everything. The simplest form of a conditional is a basic if statement. In the AP exam's pseudocode, and yes, College Board uses their own pseudocode style, not Python or Java, it looks like this. If, condition, block of statements. Think of it like a bouncer at a club. The condition is the rule. Are you on the list? If yes, you get in and those statements execute. If no, the bouncer just lets you walk right past that block of code. No drama, no error. It simply skips it entirely. This is a crucial point for the exam. If the condition is false and there's no else clause, nothing happens. The program doesn't crash. It doesn't get confused. It just moves on. Students lose points all the time by assuming a missing else means something will break. It doesn't. If else. Two roads diverging. Now let's give our bouncer a second door. The if-else structure means that something always happens. Either the if block runs or the else block runs. One of them will always execute. In College Board pseudocode, if, condition block of statements executed, if condition is true, else block of statements executed if condition is false. Here's a beautiful real-world analogy. Imagine a thermostat. If the temperature is below 68 degrees, the heat turns on. Otherwise, the heat stays off. There's no third option. The system always does one of those two things. The if-else structure guarantees that exactly one branch runs every single time. On the multiple choice section, exam writers love to test whether you understand which block runs under specific conditions. When you see a question like this, trace through it slowly. Plug in the given value. Evaluate the Boolean condition, and follow the correct branch. Resist the temptation to rush. Conditional tracing is one of the highest frequency MCQ topics on this exam. Nested conditionals. Decisions inside decisions. Here's where it gets wonderfully layered. A nested conditional is simply a conditional statement inside another conditional statement. Think about ordering at a coffee shop. If you want coffee, then, if you want it iced, the barista makes an iced coffee, otherwise they make a hot coffee. If you didn't want coffee in the first place, neither of those inner branches ever fires at all. In pseudocode, nesting looks like if blocks living inside other if or else blocks. The AP exam will absolutely test your ability to trace through nested logic, so practice reading these from the outside in. The outer condition must be true before the inner condition even gets checked. This is an edge case that trips up a lot of students. They assume the inner condition can be evaluated independently, but it can't. The outer gate has to open first. Boolean conditions and relational operators. Your conditions aren't just yes or no magic, they're built from relational operators. College Board's pseudocode uses the operators you'd expect. For equality, note, this is equal to not assignment in most contexts on the exam. You can not equal, and greater than or equal. You can also build compound conditions using and, or, and not. Here's the trap that appears on almost every exam, the difference between and or. If you use and, both conditions must be true for the whole thing to be true. If you use or, at least one must be true. So x is greater than 5 and x is less than 10 means x is between 5 and 10, both conditions required. But x is less than 5 or x greater than 10 means x is outside that range, either condition is enough. Students frequently mix these up under pressure, especially with boundary values. Always check what happens when x equals exactly 5 or exactly 10 in those expressions. Those boundary conditions are favorite MCQ territory. The not operator simply flips the Boolean value. Not x equals 5 is the same as x is not equal to 5. On FRQ responses, being able to correctly rewrite conditions using not can sometimes simplify your logic and earn you style points. But more importantly, misusing not is one of the most common sources of logical errors students make. Common traps to avoid on the AP exam. One of the sneakiest traps involves overlapping versus mutually exclusive conditions. If you write two separate if statements back to back rather than an if-else, both conditions get checked independently, and both blocks could execute if both conditions happen to be true at the same time. But if you use if-else, only one block ever runs. Know the difference. Cold exam questions will deliberately set up scenarios where this distinction changes the output entirely. Another trap. Make sure you're evaluating conditions in order. In a chain of nested if-else-if structures, once a true condition is found and its block executes, the rest of the chain is skipped entirely. If the first condition catches a case you didn't intend, your later conditions never get a chance to run. Connections to other units. Conditionals don't live in isolation. They're the backbone of almost everything else you'll study. In Unit 3, they connect directly to iteration. Loops often use Boolean conditions to decide when to stop. In Unit 4, when you're analyzing algorithms and their efficiency, the branching paths created by conditionals affect how many steps a program takes. In Unit 5, when you start thinking about how programs behave in edge cases and how to find errors, conditional logic is almost always at the center of the bug. And when you work with lists and data in Unit 3 as well, filtering data, finding elements that meet certain criteria, is really just conditionals applied repeatedly. The ability to read, trace, and write conditional logic is arguably the single most tested programming skill on this exam, appearing in both the multiple choice and free response sections every year, without exception. With conditionals firmly in your toolkit, you're ready to take the next step, because once your code can make decisions, the natural question becomes, what if it needs to make the same decision over and over again? That's exactly where iteration comes in. 3.7 Nested Conditionals. What are nested conditionals? Picture yourself at a coffee shop, which is exactly where we are right now. So let's lean into this. You walk up to the counter, and the barista asks, do you want a hot or iced drink? You say, hot. Now, because you said hot, they ask a follow-up question. Do you want coffee or tea? And because you said coffee, they ask yet another. Do you want a latte or a drip? Each question only gets asked because you gave a particular answer to the one before it. That right there is nested conditionals in action, a decision inside a decision inside a decision. In AP Computer Science Principles, a nested conditional is exactly what it sounds like, a conditional statement that lives inside another conditional statement. The College Board defines it as a conditional statement that appears within the body of another conditional. When the outer condition is true or false, the program doesn't just execute one action. It evaluates an additional condition before deciding what to do. You're layering logic, stacking decisions on top of one another like a branching tree. The pseudocode structure the College Board uses on the AP exam looks like this. You have an outer if block, and inside the then clause, or the else clause or both, you find another complete if-else structure. In AP pseudocode, it might look like if condition 1, if condition 2, less than block of statements, else block of statements, else block of statements. Every if belongs to its own complete logical unit. The inner if only runs when the outer if's condition evaluates to true. That dependency relationship is the heart of what makes nested conditionals powerful and what makes them tricky. The flow of execution. Trace it like a flowchart. Here's where visualization becomes your best friend on the exam. Think of a nested conditional as a flowchart shaped like a tree growing downward. You start at the root, the outermost condition, and you follow one of two branches, the true path or the false path. If you take the true path, you arrive at another diamond-shaped decision box, the inner condition. From there, you branch again. The false path from the outer condition might skip that entire inner structure entirely and go somewhere else. When the College Board asks you to trace through nested conditional code, you should literally draw this tree on your scratch paper. Draw a diamond for each condition. Label the outgoing arrows true and false, and write what happens at each endpoint. This technique is called tracing, or desk checking, and it is arguably the single most tested skill in this section of the exam. Students who skip this step and try to see the logic in their head make far more mistakes on MCQs, a critical boundary condition to watch for. What happens when the outer condition is false? The answer is that the inner conditional is completely skipped. The program never even evaluates it. This is one of the most common wrong answer traps. An exam question might ask you what happens to variable x when a certain set of inputs is given, and if those inputs cause the outer condition to fail, the inner conditional is irrelevant. Students who don't trace carefully will accidentally apply the inner conditional's logic when they shouldn't, and they'll pick the wrong answer every time. Nested conditionals versus sequential conditionals. A critical distinction. The College Board loves to test whether you can distinguish nested conditionals from a series of separate sequential if statements. These are genuinely different structures with genuinely different behavior, and confusing them is one of the most common conceptual errors students make. Imagine you're grading a student as either passing or failing, and then, if they're passing, determining whether they earned an A, B, or a C. If you write separate if statements for each grade category without nesting them, every single condition gets evaluated every single time, regardless of whether the student passed. That wastes computational steps and, more importantly, can produce incorrect results. With proper nesting, you check whether they passed first, and only if they passed do you bother checking the letter grade. The inner conditions are gated behind the outer one. The College Board also distinguishes nested conditionals from the use of logical operators like and or. For example, if score is greater than or equal to 60, and score is less than 70, accomplishes something similar to nesting, but the structure is fundamentally different. On the exam, you may be asked to rewrite a nested conditional using a logical operator or vice versa, so understanding both forms and knowing they can sometimes express the same logic is essential for a 5. Real-world analogy, the airport security lane. Let's make this stickier with another analogy. Think about airport security. First, a gate agent checks whether you have a boarding pass. If you don't, you're turned away. The process ends there. But if you do have a boarding pass, you move forward to a second checkpoint where an agent checks your ID. If your ID is invalid, you're stopped there. If it's valid, you proceed. Now you're in a third check. You either have TSA pre-check or you don't, which determines which screening lane you enter. Each of these decisions only happens because you successfully cleared the one before it. Remove any one of those outer conditions, and the inner checks become meaningless. That's nested conditionals as real infrastructure. Connections to other units. Nested conditionals don't live in isolation. They connect deeply to other units you've studied. In Unit 3, they build directly on 3.5 and 3.6, where you learned basic conditionals and Boolean expressions. Every condition inside a nested structure is still a Boolean expression evaluating to true or false, so your skills with relational operators and logical operators feed directly into this topic. Looking forward, nested conditionals become critical scaffolding for understanding algorithms more broadly, Unit 3, and program design questions on the create performance task. When you write or analyze an algorithm with multiple decision points, you're almost certainly dealing with nesting. On the FRQ portion of the exam, the scoring rubric often awards specific points for correct conditional logic, and examiners look carefully at whether your inner conditions are properly nested or incorrectly written as flat sequential statement. Finally, nested conditionals appear frequently in abstractions and procedures Unit 3.12 to 3.30, where functions may contain complex branching logic internally. Understanding how to read and trace that logic is non-negotiable for the exam. What to remember for exam day. Before you move on, lock in these 3 things. First, always trace nested conditionals step by step. Never eyeball them. Second, remember that a false outer condition means the inner conditional never runs, not even once. Third, know that nested conditionals and logical operators can sometimes express equivalent logic, and the exam will absolutely test your ability to convert between them. With nested conditionals in your toolkit, you're ready to tackle one of the most elegant and powerful ideas in programming, the loop. Next up, we'll explore how computers repeat actions efficiently using iteration, and you'll see how conditionals and loops combine to create algorithms of remarkable complexity. 3.8 Iteration. Loops. What is iteration really? Picture this, you're making a batch of chocolate chip cookies. You don't just make one cookie and call it a day. You repeat the same set of actions over and over. Scoop the dough, place it on the pan, repeat until the tray is full. That repeated process, that's iteration in a nutshell. In computer science, iteration means executing a block of code multiple times, and it's one of the most powerful ideas in all of programming. Without loops, your programs would have to manually list every single step, one by one, for every single piece of data. With loops, you write the instructions once and let the computer do the repetition. This is the heart of why computers are so extraordinarily useful. They don't get bored, they don't get tired, and they're perfectly happy running the same code a million times without complaint. The 2 flavors of loops the AP exam cares about. The College Board's pseudocode, the standardized notation you'll see on the actual exam, uses 2 primary loop structures, and you need to be deeply comfortable with both. The first is the repeat in times loop. This is your I know exactly how many times I want to do this loop. Think of it like setting a kitchen timer. You decide up front how many repetitions you need. The loop counts them for you, and when it hits that number, it stops. In AP pseudocode, it looks like this. Repeat n times, lack of statements. The code inside the curly braces executes exactly n times, no more, no less. If n is 0, the block never runs at all, and that's an important edge case we'll come back to. The second is the repeat until loop. This one is driven not by a count, but by a condition. It keeps going until some condition becomes true. The AP pseudocode form is repeat until condition block of statements. Imagine you're searching through a pile of papers for a specific document. You keep flipping through pages until you find the one you need. You didn't know in advance how many pages you'd have to look through. You just knew when to stop. That's the repeat until logic exactly. The critical difference, condition checking timing. Here's where many students get tripped up on the MCQ section, so pay close attention. The repeat until loop in AP pseudocode checks its condition at the end of each iteration, meaning the body of the loop always runs at least once before the condition is ever evaluated. This is the equivalent of what some programming languages call a do-while loop. Compare this to a condition checked at the beginning of a loop, where it's possible the code inside never runs at all if the condition is already false from the start. Why does this matter for the exam? Because if you see a question where a repeat until loop is used, and you need to figure out the final state of a variable, remember that first pass through the loop body happens unconditionally. The condition is only your exit check, and it gets asked after the work is done. Miss that timing, and you'll be off by one iteration, a classic trap in College Board MCQs. Tracing through a loop, the method that saves points. The single most reliable skill you can develop for loop-related exam questions is variable tracing. When you see a loop in a problem, grab a scratch piece of paper and build a small table. Label columns for each variable involved, plus a column for the iteration number or loop counter. Then walk through the loop step by step, updating each variable as you go. This systematic approach prevents the I did it in my head and got confused error that costs so many students points. Say you have a variable total initialized to 0, and a repeat 4 times loop that adds the loop counter to total each pass. Iteration 1, total becomes 1. Iteration 2, total becomes 3. Iteration 3, total becomes 6. Iteration 4, total becomes 10. That table building habit is how you catch every boundary condition with confidence rather than guessing. Infinite loops, the danger zone. A particularly important concept the AP exam tests is the infinite loop. A loop whose exit condition is never satisfied, so it runs forever, or until the program crashes. With repeat in times, you can't create an infinite loop because the count is fixed. But with repeat until, if the condition can never become true given the logic inside the loop, you're stuck. For example, if your condition is checking whether a variable equals 10, but the loop is only ever adding 2 to an odd number, you'll skip right past 10 and keep going forever. On the AP exam, you might be asked to identify which version of a loop will run correctly versus which creates an infinite loop. Always check whether the loop body actually moves the program towards satisfying the exit condition. Connecting loops to the bigger picture. Iteration doesn't exist in isolation. It's deeply woven into nearly every other AP CSP concept. When you study list traversal in Unit 3, you're using loops to move through every element in a list, which is one of the most commonly tested programming patterns on the exam. The College Board calls this accessing each item in a list in order, and it almost always involves a loop paired with an index variable. You'll also see loops appear in searching and sorting algorithms. The entire concept of linear search is built around repeating a comparison for each element until you find a match or exhaust the list. Loops also connect directly to the efficiency and correctness ideas in Unit 4's discussions of algorithms. A loop that runs n times has a relationship to input size that matters when thinking about how fast or slow a program is, which ties into broader discussions of algorithmic efficiency. And in the impact of computing sections, loops are the mechanism behind processing massive data sets, the kind of data analysis that powers everything from Netflix recommendations to weather forecasting. The exam traps to watch for every time. 3 traps appear on AP CSP loop questions more than any others. First, off by 1 errors. Check carefully whether a loop runs the expected number of times, especially when conditions involve greater than versus greater than or equal to. Second, initial variable values. Always check what a variable is set to before the loop begins, because that starting value dramatically changes the output. Third, loop body scope. Make sure you know exactly which lines of code are inside the loop versus outside it. In AP pseudocode, the curly braces define this, and a misread there can completely change your answer. Master those 3 checks, and you've diffused the most common MCQ bombs in this entire section. With loops now firmly in your toolkit, you're ready to see them applied in one of their most powerful real-world uses, because next up, we're diving into how computers traverse and manipulate lists, where everything you just learned about iteration becomes the engine driving some of the most elegant and important algorithms in computer science. 3.9 Developing Algorithms. Let's talk about one of the most satisfying skills in all of computer science, the ability to take a messy, complicated problem and break it down into a precise step-by-step solution. That's what algorithm development is all about, and it's the backbone of everything you'll do in this course and on the AP exam. What is an algorithm really? The College Board defines an algorithm as a finite set of instructions that accomplishes a specific task. Notice, every word in that definition matters for the exam. It must be finite, it has to eventually stop, it must be a set of instructions, vague intentions don't count, and it must accomplish a specific task, there's a goal at the end. Think of it like a recipe. A good recipe tells you exactly what to do, in what order, and it ends when the dish is done. A bad recipe that says cook until it tastes right is not an algorithm, it's wishful thinking. For the AP exam, you need to know that algorithms can be expressed in 3 ways: natural language, plain English descriptions, flowcharts, visual diagrams using shapes and arrows, and pseudocode, a structured language that College Board uses throughout the exam. You will see all 3 on the multiple choice section, and you need to be fluent in reading and interpreting each one. The 3 building blocks of every algorithm. Here's something powerful. Every algorithm ever written, from the code running your phone to the software guiding a spacecraft, is built from just 3 fundamental constructs. College Board calls these sequencing, selection, and iteration, and knowing the difference between them cold is absolutely essential for your exam. Sequencing is the simplest. It means instructions execute in order, one after another, top to bottom. If you're making a sandwich, you get the bread before you spread the peanut butter. The order matters, and steps happen exactly once in the sequence given. On the exam, tracing through a sequential block of code is your most basic skill. Just follow the instructions in order and track the values of your variables. Selection is where your algorithm makes a decision. This is your if-else logic. Imagine you're at a coffee shop, and the menu says, if we have oat milk, add oat milk. Otherwise, add regular milk. The algorithm branches based on a condition. The key thing College Board wants you to understand is that in a selection statement, only one branch executes, not both. This sounds obvious, but it's a common trap on multiple choice questions where students think both paths run. Iteration means repeating a block of instructions. This is your loop, a repeat or repeat until construct in College Board pseudocode. Think of iteration like rinsing your hair. You lather, rinse, and repeat until the shampoo is out. The loop keeps going until a condition is met or a set number of repetitions is reached. Here's where students often stumble. You need to trace through loops carefully, counting iterations and tracking variable values at each step. The exam loves asking what a loop outputs after a specific number of repetitions, and off by one errors are one of the most common wrong answers in the multiple choice section. Developing algorithms from scratch. The AP exam doesn't just ask you to read algorithms, it asks you to think about how you'd build one. The College Board framework here is that you develop algorithms by combining these three constructs to solve problems. A great mental model is to ask yourself 3 questions before writing any code. What needs to happen in order? Where does my program need to make a choice? And where does something need to happen more than once? Think about an algorithm to find the largest number in a list. You don't see the whole list at once. You're reading through it like cards in your hand. You keep track of the biggest number you've seen so far. That's a variable you initialize before the loop. And for each new number you encounter, that's iteration. You check whether it's bigger than your current maximum, that's selection. And if so, you update your maximum. Walk through that logic step by step, and you've built a classic algorithm from scratch. The exam will absolutely give you variations of this, finding a minimum, computing a sum, counting occurrences of a value, and they all follow this same mental template. Tracing algorithms and avoiding common traps. Tracing is your best friend for the exam. When you're given an algorithm and asked what it outputs or what a variable's value is, slow down and do it by hand. Write out a table with each variable as a column and update it step by step. The most dangerous thing you can do on a trace question is try to do it in your head. That's where mistakes happen. Here are the traps that appear most often. First, watch for the scope of your variables. If a variable is set inside a loop, ask yourself whether it resets on every iteration or persists across iterations. Second, watch for off-by-one errors in repeat loops. If pseudocode says repeat 4 times, the body executes exactly 4 times, not 3, not 5. Third, watch for conditions in repeat until loops. The loop continues until the condition is true, meaning it keeps running while the condition is false. Students who confuse this with while loops get the termination condition exactly backwards. Another trap involves nested constructs, a loop inside a loop, or a selection inside a loop. For nested loops, the inner loop completes all its iterations for every single iteration of the outer loop. If you have a loop that repeats 3 times containing a loop that repeats 4 times, the inner body executes 12 times total. The exam will test this. Connections across the course. Algorithm development doesn't live in isolation, it threads through the entire course. In Unit 2, when you study abstractions, you're seeing how algorithms can be packaged into named procedures that hide their complexity. In Unit 4, when you study lists and data structures, every list traversal algorithm uses the sequencing, selection, and iteration constructs you've mastered here. In Unit 5, when you study programming, you're implementing these algorithms in actual code. And in Unit 6, when you explore the internet, network routing protocols are themselves algorithms for finding paths through a network. Even the innovation discussions in Unit 7 often hinge on how an algorithm processes data. For the free response portion, remember that when you're asked to write or modify an algorithm, College Board is looking for correct use of pseudocode syntax, logical correctness, and all 3 constructs used appropriately. You won't lose points for imperfect pseudocode syntax as long as your logic is clear, but precision always helps. The ability to develop, trace, and refine algorithms is honestly the heartbeat of this entire course. And as you'll see next, that skill becomes even more powerful when you learn how to package your algorithms into reusable, modular procedures. 3.10. List operations, traversal, insert, append, remove, length. Imagine you're a librarian managing a shelf of books. You need to know how many books you have, find a specific one, add new arrivals, and occasionally pull a damaged book off the shelf. That's exactly what list operations do in programming, and in AP Computer Science Principles, mastering this topic is non-negotiable for scoring that 5. Lists are the backbone of nearly every algorithm you'll encounter, so let's dig in together. What a list actually is in AP CSP. A list is an ordered sequence of elements. Think of it like a numbered playlist on your phone. Each song has a position, and that position matters. The College Board calls each position an index, and here's the single most important thing you need to tattoo on your brain right now. AP CSP uses one-based indexing. That means the first element in a list is at index 1, not index 0. This is different from most real programming languages like Python or JavaScript, which start at 0. This distinction is the number 1 trap on the multiple choice section. When you see pseudocode on the AP exam, assume index 1 is the first element, always. If you have a list called MyList containing the values 10, 20, 30, 40, then MyList 1 is 10, MyList 2 is 20, and so on. Simple enough, but the exam will absolutely try to catch you assuming otherwise. The length operation. The length MyList function returns the total number of elements in the list. Using our 4-element example, length MyList returns 4. This becomes critically important when you're traversing a list because you need to know where to stop. One edge case that appears on exams is the empty list. If a list has no elements, length mylist returns 0, and any attempt to access mylist1 on an empty list would cause an error. Keep that in mind. The exam loves to ask what happens at the boundaries. Traversal, the heart of list processing. Traversal means visiting every element in a list, one by one, usually to do something with each one, check a condition, add values together, print them out, whatever the algorithm demands. The standard AP exam pseudocode for a complete traversal looks like a for each loop. For each item in mylist processes every element from first to last automatically. This is clean and elegant. You'll also see traversal written with a repeat loop, using an index variable, something like repeat length mylist times with a counter going from 1 up to the length. Both approaches accomplish the same thing, but the for each loop is simpler and less prone to off-by-one errors, which brings us to another classic exam trap. If you manually loop using an index and you start at 0 instead of 1, or you go up to length plus 1, you'll either miss an element or go out of bounds. The exam will present you with subtly broken traversal code and ask you to identify the error. Always double-check that your loop boundaries align with one-based indexing. Partial traversal is also fair game. Sometimes you only want to process elements up to a certain point, say, the first half of a list, and the AP exam may ask you to trace through that code carefully. Insert, append, and remove. Now let's talk about modifying a list, because this is where students often get tangled up. Insert mylist I value adds a new element at position I, shifting everything at or after that position one spot to the right. Imagine squeezing a new book onto the middle of your shelf. Everything to the right of where you insert has to scoot over. After insertion, the length increases by 1. Here's a key exam moment. If you insert at position 1, the new element becomes the first item and everything else shifts right. If you try to insert at an index beyond the current length plus 1, that's an invalid operation. Append mylist value adds a new element to the very end of the list. This is the simpler cousin of insert. No shifting required, nothing moves. You're just tacking something onto the end. Length increases by 1. You can think of append as insert mylist, length mylist plus 1, value. They're equivalent when adding to the end. And recognizing that equivalence can help you on a tricky question. Removed mylist, I deletes the element at position I and shifts everything after it one spot to the left to close the gap. Length decreases by 1. Here's a boundary condition the exam loves. If you remove the last element, nothing needs to shift. You just shrink the list by 1. If you try to remove from an empty list or use an index that doesn't exist, that's an error condition. A common FRQ mistake is forgetting that after a remove, the indices of subsequent elements change. Say you're iterating through a list and removing elements as you go. If you remove index 3, what was index 4 is now index 3. If your loop counter keeps moving forward, you'll accidentally skip elements. This is a subtle bug the College Board has tested explicitly, and recognizing it in code is worth points. Connecting to other units, lists don't live in isolation. In Unit 2, you learned about variables. A list is just a variable that holds multiple values instead of one. In Unit 3's broader algorithms section, lists power searching and sorting algorithms like sequential search and binary search. When you study those topics, every single one involves list traversal. In the create performance task, if your program doesn't use a list in a meaningful way, storing data, processing it with an algorithm, you will lose points on the scoring rubric, because a list that stores and processes data is explicitly required. The exam also connects lists to abstraction. A list lets you represent a collection of related data as a single named object, which is a fundamental programming abstraction. The big picture before you move on. Here's your quick mental checklist. Lists are 1 indexed in AP exam pseudocode, not 0 indexed. Length tells you how many elements exist and prevents you from going out of bounds. For each, traversal hits every element cleanly. Insert shifts elements right, append adds to the end, and remove shifts elements left, and in all 3 cases, the length changes by 1. Edge cases like empty lists, inserting at the first or last position, and removing while traversing are prime MCQ territory. Coming up next, we'll explore string operations and how the AP exam treats text as a sequence of characters, which you'll notice is a lot like treating a string as a list of individual letters, so your new list knowledge is already paying dividends. 3.11 Binary Search. The phone book problem. Let me paint you a picture. You're standing in a library, and someone hands you an old-fashioned phone book, the kind with 10,000 names listed alphabetically. They ask you to find Sarah Mitchell. Now you have 2 options. You could start at page 1 and flip through every single entry until you find her. That's called a linear search, and honestly, it's exhausting. Or, and this is the clever move, you could flip straight to the middle of the book, see that you've landed on names starting with L, realize that Mitchell comes after L, and immediately throw away the entire first half of the book. You've just cut your problem in half in a single move. Do that again and again, and you'll find Sarah Mitchell in a fraction of the time. That elegant strategy is the heart of binary search, and it's one of the most powerful ideas in all of computer science. On the AP exam, you need to understand not just what binary search is, but when it works, how it works, exactly how efficient it is, and what can go wrong. Let's walk through all of it together. What binary search actually does, Binary search is a search algorithm that works by repeatedly dividing a sorted list in half. I want you to notice that word sorted. It is absolutely non-negotiable. Binary search only works on data that has already been organized in order, whether that's ascending numbers, alphabetical names, or any other consistent ordering. If you try to run binary search on an unsorted list, you'll get garbage results, and the AP exam absolutely loves to test this precondition. If a question asks you whether binary search can be applied to a given dataset, your first thought should always be, is this data sorted? Here's the step-by-step process College Board expects you to know. You start by examining the middle element of the list. If that middle element is the value you're looking for, congratulations, you're done. If your target value is less than the middle element, you discard the upper half of the list and repeat the process on the lower half. If your target is greater than the middle element, you discard the lower half and repeat on the upper half. You keep having and searching until you either find your target or determine that it isn't in the list at all. Finding that middle index is something the exam tests concretely. If you have a list with indices from a low boundary to a high boundary, the middle index is calculated as the integer result of low plus high divided by 2. If the list has an even number of elements, you'll land on one of the two middle positions. College Board typically uses the lower of the two middle indices when the list has an even length, but the key point is that you must be consistent and methodical. The efficiency formula you must know. Here's where things get beautifully mathematical, and yes, this shows up on the exam. The efficiency of binary search is described as logarithmic, written as log base 2 of n, where n is the number of elements in your list. What does that mean in plain English? It means the maximum number of steps you'll ever need to find any element or determine it's missing is log base 2 of n. Think about what that means in practice. If you have a list of 8 elements, binary search needs at most 3 steps because 2 cubed equals 8. A list of 16 elements, at most 4 steps. A list of 1,024 elements, at most 10 steps. A list of 1 billion elements, only about 30 steps. Compare that to linear search, which could theoretically check all 1 billion elements, and you start to feel the magic. The AP exam may ask you to identify how many steps binary search requires for a given list size, so make sure you're comfortable working with powers of 2 in both directions, converting between the exponent and the resulting list size. Tracing through an example. Let's make this concrete. Suppose you have a sorted list, 3, 7, 12, 19, 25, 31, 44, 58. Your target is 25. The list has 8 elements, so your indices run from 0 to 7. Your middle index is 0 plus 7 beloved by 2 equals 3, which gives you the value 19. Is 25 equal to 19? No. Is 25 greater than 19? Yes. So you discard everything at index 3 and below. Now your search range is indices 4 through 7, giving you the sublist 25, 31, 44, 58. Your new middle index is 4 plus 7 slash 2 equals 5, which gives you the value 31. Is 25 equal to 31? No. Is 25 less than 31? Yes. So you discard everything at index 5 and above. Now your search range is just index 4, giving you the value 25. Middle index is 4, value is 25. That's your target. Found it in 3 steps. The AP exam loves to give you a list and ask you to trace through binary search step by step, identifying which element is checked at each stage. Practice this methodically, always recalculating your middle index based on your current boundaries, and you'll handle those questions with confidence. Edge cases and classic exam traps. Now let's talk about the sneaky stuff. The most common trap on the AP exam is a question that presents an unsorted list and asks whether binary search will successfully find an element. The answer is that binary search might appear to work occasionally by chance, but it is fundamentally unreliable on unsorted data. It is not a valid application of the algorithm. Always flag unsorted data as a disqualifier. Another common trap involves searching for an element that is not in the list. Binary search handles this gracefully. When your low boundary exceeds your high boundary, you know the element isn't present, but students sometimes think binary search can only work if the element exists. Not true. Correctly determining that an element is absent is a valid and successful outcome of the algorithm. Watch out also for questions about the number of comparisons. Sometimes the exam asks for the maximum number of comparisons for a specific list size, and students confuse log base 2 at n with log base dense at n, or simply with n. Remember, it's always log base 2 because you're dividing by 2 at each step. Connections across the course. Binary search connects directly to your understanding of algorithm efficiency from Unit 3, where you compare algorithms based on how their running time grows with input size. It also ties into the broader theme of abstraction. Binary search works on any sorted data regardless of what that data represents, which is a beautiful example of a generalizable algorithm. When you get to discussions of data and lists in Unit 2, you'll recognize that the requirement for sorted data is a precondition that must be established before the algorithm can run, connecting search algorithms to data organization and preparation. Some AP practice questions also ask you to compare binary search to linear search in terms of correctness and efficiency, so understanding both algorithms side by side is essential. Binary search is one of those ideas that feels almost too simple once you understand it, yet it's the foundation of incredibly powerful real-world systems. From database indexing, to autocomplete features, to the way your computer locates files. With that foundation locked in, let's move forward and explore how we evaluate and compare the efficiency of different algorithms more formally, which is exactly where Unit 3 takes us next. 3.12 Calling Procedures. What it means to call a procedure. Imagine you're at a coffee shop, and you tell the barista, "Make me a latte." You don't walk behind the counter and steam the milk yourself. You just make the request, pass along any details they need, like oat milk, please, and then you wait for the result. That's exactly what calling a procedure is. In programming, a procedure is a named block of code that performs a specific task, and calling that procedure is simply the act of invoking it, telling your program to go execute that block of code. You, the caller, just hand over any necessary information, and the procedure does its job. The College Board uses the term procedure as a broad umbrella. In different programming languages, you might hear this called a function, a method, a subroutine, or a module. For the AP exam, stick with procedure. When you see a question referencing a procedure, know that it means a defined, reusable block of code that can be called from other places in a program. Parameters, arguments, and the art of passing information. Here's where many students start to trip up, so let's slow down and be precise. A parameter is the variable listed in the procedure's definition. It's the placeholder. An argument is the actual value you pass in when you call the procedure. Think of the procedure definition as a recipe that says, you will need 1 cup of flour. That's the parameter, a placeholder. When you actually bake and you measure out your real cup of flour, that's the argument. In the AP pseudocode you'll see on the exam, a procedure call looks like this. Procedure names argument 1, argument 2. The arguments get matched to the parameters in order. First argument maps to the first parameter, second to the second, and so on. This is called positional correspondence, and it matters enormously. If a procedure is defined to take a name and then an age, and you call it with an age first and a name second, the procedure will treat the number like a name and the name like a number. The computer won't yell at you during an exam question. It will just behave in unexpected ways, and you'll need to trace through carefully to see what actually happens. Return values, getting something back. Some procedures give you something back. These are called procedures that return a value, and on the exam, the College Board will often distinguish between procedures that simply perform an action versus those that return a value. When a procedure returns a value, that value can be stored in a variable, used in an expression, or even passed as an argument to another procedure. In AP pseudocode, you'll see return expression inside the procedure, and when the procedure is called, the entire call expression evaluates to whatever was returned. Picture it like a vending machine. You press the button, that's the call. You might pass in $1, that's your argument. The machine returns a bag of chips, that's the return value. You can then eat the chips immediately, save them for later, or hand them to someone else. In code, you can use the return value right away in a calculation, assign it to a variable for later, or pass it directly into another function call. One critical edge case the exam loves to test. If a procedure doesn't have a return statement, or if execution reaches the end of the procedure without hitting one, the procedure returns nothing, and if you try to use that nothing as a value, your program will behave incorrectly. Watch for questions that show a procedure missing a return statement, and then ask what value gets stored in a variable. The trap answer is whatever value the procedure seems to compute. The correct thinking is that without return, no value comes back. Tracing through procedure calls. The AP exam frequently asks you to trace through code that involves procedure calls, and this is where your careful, methodical thinking earns you points. When a procedure is called, execution jumps to the procedure's code. Any parameters take on the values of the arguments. The procedure runs line by line. When it finishes or hits a return, execution jumps back to where the call was made. And if there's a return value, it replaces the procedure call in the expression. A classic MCQ trap involves nested calls, one procedure calling another, say double x returns x2 and ADD1E, x returns x plus 1. What does double ADD1E3 return? You work from the inside out. ADD1E3 returns 4, then double 4 returns 8. The trap is working outside in and getting 7. Always evaluate the innermost call first, just like you do with nested parentheses in algebra. Why this connects to everything else. Calling procedures is honestly the backbone of the rest of this course. When you study abstractions in Unit 4, you'll see that procedures are one of the primary tools programmers use to manage complexity. You hide the details inside a procedure and just call it by name. When you analyze algorithms in Unit 3 and 4, nearly every algorithm is expressed as a procedure. In the Explore Performance Task context, understanding how procedures work lets you describe what your program does with precision. And when the exam asks you about program correctness, whether a program does what it's supposed to, you'll need to trace through procedure calls to verify behavior. Understanding that procedures allow code to be reused without being rewritten is also tied directly to the big idea of abstraction. Instead of copying the same 10 lines of code 50 times, you write it once, name it, and call it. This reduces errors, makes programs easier to read, and makes updates dramatically easier. That's not just a coding best practice, that's a concept College Board explicitly tests in both multiple choice and free response. FRQ, scoring reminders and final watchouts. On the free response section, if you're asked to write a procedure call, make sure you spell the procedure name exactly as given, pass the arguments in the correct order, and use the return value appropriately if the question requires it. Partial credit is often awarded for correct procedure calls, even if other parts of your response have errors, so don't leave them blank. One more trap worth naming. Students sometimes confuse defining a procedure with calling a procedure. Defining creates the blueprint. Calling executes it. A procedure that is defined but never called never runs. If an exam question asks what happens when a program executes and a procedure is defined but not called, the answer is that code never runs. With a solid understanding of how calling procedures works, parameters, arguments, return values, and tracing through calls, you're perfectly positioned to tackle the next layer of complexity. What happens when a procedure calls itself, which is the fascinating world of recursion. 3.13 Developing Procedures. What is a procedure, really? Let's start with a mental image. Imagine you're a barista at a coffee shop, and every single morning, someone walks in and orders the same complicated drink, a double-shot oat milk latte with 2 pumps of vanilla and extra foam. Now, you could reinvent the process from scratch every time, asking yourself, okay, what do I do first? Grind the beans? Steam the milk? Or, and this is the key insight, you could write down the steps once, give that recipe a name, and just call the recipe every time someone orders. That's a procedure in AP Computer Science Principles. A procedure is a named group of programming instructions that may take in parameters and may return a value. It's a reusable block of code you define once and invoke whenever you need it. College Board wants you to be precise about this definition. A procedure is also called a function in many languages. The AP exam may use both terms, though procedure is the official College Board vocabulary. When a procedure returns a value, you'll sometimes see the term function used more specifically, but don't let that trip you up. On the exam, treat them as the same concept, unless the question specifically distinguishes them. Parameters and arguments. 2 words that mean almost the same thing, but don't. Here's one of the most reliable MCQ traps on this topic, so pay close attention. Parameters are the variables listed in the procedure's definition. They're the placeholders, the empty cups waiting to be filled. Arguments are the actual values you pass in when you call the procedure. When you define prosciutto or make drink size flavor, then size and flavor are parameters. When you actually call make drink large vanilla, then large and vanilla are the arguments. Students mix these up constantly, and College Board absolutely knows it. If an MCQ asks you what the parameter is, they want the variable name in the definition, not the value passed in. Why procedures matter, abstraction and modularity. Here's where this topic connects directly to one of the biggest themes in the entire AP CSP course, abstraction. Developing procedures is one of the primary ways programmers manage complexity. Think about your phone. When you tap the camera app, you're not writing code to access the lens sensor, calibrate focus, and compress the image into JPEG format. All of that complexity is hidden behind a single tap, a beautifully abstracted procedure someone else wrote. That's the power here. College Board frames this under the concept of procedural abstraction, which means you can use a procedure without needing to know how it works internally. You just need to know what it does, what inputs it needs, and what it gives back. This connects directly to Unit 3's broader discussion of abstraction and to Unit 5's exploration of the impacts of computing. Because modular, reusable code is literally what makes large-scale software possible. Procedures also enable modularity, which means you can break a large program into smaller, manageable pieces. Each procedure handles one job. This makes your program easier to read, easier to test, and easier to fix. On an FRQ, if you're asked to write or analyze code, showing that you understand why a procedure is useful, not just how to write one, can earn you interpretation points on the rubric. Writing and calling procedures in AP pseudocode. Let's talk mechanics. Because the AP exam uses its own pseudocode syntax and you need to be fluent in it. Here's the structure. College Board expects prosciutto procedure name parameter 1, parameter 2, followed by the block of instructions inside curly braces, or if the procedure returns a value, it uses return expression inside the body. A procedure that doesn't return anything simply executes its instructions and stops. A procedure that does return a value can be used inside expressions or assigned to a variable like result calculate area 510. Notice that arrow is the AP pseudocode assignment operator. Don't write equals and expect full credit on an FRQ. A critical edge case the exam loves. What happens if a return statement is encountered in the middle of a procedure? The procedure stops immediately and sends back that value. Any code after the return in that execution path is never reached. This is a classic MCQ trap where they show you a procedure with a return buried inside a conditional, and you have to trace exactly when execution stops. The difference between procedures with and without return values. Think of a procedure without a return value like a text message you send. It does something, delivers information, changes state, but you don't get anything back. A procedure with a return value is more like asking a friend a question. you input something and you get an answer you can actually use. On the AP exam, if a question shows you a procedure call being assigned to a variable, like xMyProcedure3, you know that procedure must contain a return statement. If the procedure just runs and does something, maybe it displays text or updates a list, there's no return value and you wouldn't assign it to a variable. Getting that logic backwards is a very common wrong answer trap. Scope. A concept students underestimate. Here's something that sneaks up on students. Scope variables defined inside a procedure are local. They exist only within that procedure. Once the procedure finishes, those variables are gone. This means if you define a variable called total inside a procedure, you cannot access total from outside that procedure. College Board may give you a code segment and ask what value a variable holds after a procedure call, and the trap is assuming that a local variable inside the procedure somehow changed a variable of the same name outside it. It didn't. They are completely separate. Connecting to the bigger picture. Developing procedures connects outward in every direction of this course. In Unit 2, you saw how data abstraction hides complexity in lists and data structures. Procedures do the same thing for instructions. In Unit 4, when you think about algorithms, procedures are literally how algorithms are implemented and made reusable. In Unit 5, the idea that software engineers collaborate on massive programs is only possible because procedures let different people write different pieces without needing to understand every line of the whole system. For FRQ scoring, always explain why a procedure is useful, not just what it does. Rubrics reward demonstrated understanding of abstraction, and saying something like, "This procedure reduces repetition and allows the code to be reused with different inputs," is exactly the kind of language that earns full marks. Now that you've got a solid grip on how to build and use procedures, let's zoom in on a technique that supercharges their power using parameters and return values together in increasingly sophisticated ways as we explore more complex algorithm design in the sections ahead. 3.14 Libraries. What is a library, really? Let's start with a story. Imagine you're building a house from scratch. You could mill your own lumber, forge your own nails, and hand blow your own window glass. Technically, nothing is stopping you, but that would be absurd. You'd spend years just getting to the point where you could lay a single wall. Instead, you go to a hardware store, someone else already made the nails, someone else tempered the glass. You just pick up what you need and build. That is exactly what a software library is. A library, in the AP Computer Science Principles Framework, is a collection of pre-written procedures, sometimes called functions or methods that programmers can call upon without having to write that code themselves. The College Board defines it simply. A library is a collection of procedures that can be used in the creation of programs. That definition is short, but it carries enormous weight on the exam, so let's unpack every piece of it. Procedures, APIs, and abstraction. The core triangle. The first thing to understand is that libraries live and die by something called an API, which stands for Application Programming Interface. Think of an API as the menu at a restaurant. You don't need to know how the chef makes the pasta. You just need to know that if you order spaghetti carbonara, something delicious arrives at your table. The API tells you what procedures are available, what inputs they expect, and what outputs they produce. It is the contract between the library and the programmer using it. This connects directly to the concept of abstraction, which is one of the most important ideas threaded through this entire course. When you use a library procedure, you're taking advantage of abstraction. You're hiding the complex implementation details underneath a clean, simple interface. You call a function like draw circle x, y radius, and a circle appears on screen. You have no idea, and more importantly, you don't need to know how the underlying code calculates every pixel along that curve. The complexity is abstracted away. For the AP exam, you need to be crystal clear that using a library is a direct application of abstraction, and that the API is what makes that abstraction usable. Why libraries matter, efficiency and collaboration. Here's a real-world connection that tends to stick. When scientists around the world study the same disease, they don't each independently invent a microscope. They use standardized tools so they can collaborate, compare results, and build on each other's work. Libraries and programming serve the same civilizational function. They allow programmers to build on the work of others rather than starting from zero every single time. The College Board wants you to understand two major benefits. First, libraries save time and reduce errors. If a library procedure has been tested by thousands of developers, it is far more reliable than code you dash off yourself at midnight before a deadline. Second, libraries enable collaboration and scalability. When a development team agrees to use the same library, everyone speaks the same language, and large software projects become manageable. The Randomness Library, your MCQ workhorse. Now, here's where it gets very exam-specific, so lean in. The AP CSP course uses a simplified programming language in its pseudocode, and within that pseudocode there is a specific procedure you're expected to know cold. Random, a B, this procedure returns a random integer between A and B, inclusive on both ends. That word inclusive is doing a lot of work, and it is one of the most reliable MCQ traps on the entire exam. If a question asks which values random 1, 5 can produce, the answer is 1, 2, 3, 4, or 5 possible values, including both endpoints. Students who are used to zero-index languages or exclusive upper bounds often miss that the College Board's random procedure includes both A and B. Do not fall into that trap. Burn this into your memory. Both endpoints are included. A typical MCQ might show you a piece of code that simulates rolling a 6-sided die and ask whether random 05 or random 16 is the correct implementation. The answer is random 16 because a standard die produces values from 1 through 6. The version starting at 0 would produce 0 through 5, which is wrong. The exam loves testing whether you can trace exactly what range a random call produces. The procedural abstraction connection. Libraries also connect deeply to the topic of writing your own procedures and using parameters. When you define a procedure in your own program, you're essentially creating a tiny personal library. The same logic applies. You define the procedure once, and then you can call it many times without rewriting the logic. The difference is that a published library is shared, documented, and available to anyone. This is why the College Board connects libraries to the broader concept of procedural abstraction. Both involve the same fundamental idea: hide complexity behind a reusable name. On the free response portion of the exam, specifically in the Create Performance task, you may be asked to explain how your program uses abstraction. If your program calls any library procedures, that is a valid and strong example of abstraction in action. Describe what the procedure does. Explain that you're not implementing it yourself, and connect it to the idea that the implementation details are hidden from view. Common misconceptions to avoid. One misconception students carry into the exam is thinking that using a library means you don't need to understand programming. Wrong. You still need to understand what inputs a procedure expects, what it returns, and how to integrate it into your logic. The API tells you what something does, but you must still understand how to use it correctly in context. Another misconception is confusing a library with a programming language itself. A language provides the syntax and structure. A library provides ready-made tools that operate within that syntax. They are distinct things also. Don't confuse the concept of a library with a data structure like a list or a database. Libraries are collections of procedures, not collections of data. That distinction shows up in multiple choice distractors. Connections across the course. Libraries thread through almost every other unit. In Unit 2, when you study data and analysis, many data science tools are themselves libraries. In Unit 5, when you explore the impact of computing, open source libraries represent a prime example of how the internet enables collaborative innovation. And when Unit 4 covers the internet and distributed systems, APIs are the mechanism by which separate software systems talk to each other across networks. Understanding libraries is not an isolated skill. It is a lens through which you understand how modern software gets built, shared, and scaled across millions of users. With that foundation locked in, you're ready to zoom out and explore some of the bigger ideas about how programs are designed, tested, and evaluated, which brings us right to the heart of how we think about correct and efficient algorithms. 3.15 Random Values. Why randomness matters in computing. Let's talk about randomness, and I promise this is more interesting than it sounds. Imagine you're building a video game, and every time a player starts a new level, the same identical maze appears in the same identical spot. Boring, right? Or imagine a password generator that always creates the exact same password. Completely useless, and honestly, a little terrifying. Randomness is what makes games feel alive, simulations feel authentic, and security systems feel secure. For the AP exam, you need to understand not just what randomness is, but precisely how College Board expects you to use it in code, and the details here are surprisingly specific. The random procedure. Get this exactly right. College Board uses one specific procedure for generating random numbers, and you need to know its syntax cold. The procedure is written as random A, B, and here is the critical definition. It returns a single value that is an integer chosen randomly from the range of integers from A to B, inclusive. That word inclusive is doing a lot of heavy lifting, and we'll come back to it in a moment, because it's the source of one of the most common MCQ traps on the entire exam. So if you write random 16, you're simulating a 6-sided die. The procedure will return 1, 2, 3, 4, 5, or 6 each with equal probability. Think of it like a perfectly fair lottery machine that draws one numbered ball from a set, every single number having an identical chance of being selected. That equal probability is built into the definition. The AP exam assumes that each value in the range is equally likely, so you never need to worry about weighted distributions or skewed randomness in this course. Inclusive boundaries, the trap that gets everyone. Here's where students lose points, and I want you to feel genuinely suspicious every time you see a random call on an exam question. The range is always inclusive on both ends. That means random 1, 10 can return 1, and it can return 10. Both endpoints are in play. This becomes especially tricky when you're trying to figure out how many possible outcomes exist. The formula for counting outcomes is simple. B minus A plus 1 commemorates or random 110 has 10 minus 1 plus 1 is equal to 10 possible outcomes. Random 3 7 has 7 minus 3 plus 1 is equal to 5 possible outcomes. The values 3, 4, 5, 6, and 7. Students who forget the plus 1 will consistently count one fewer outcome than actually exists, and that error cascades into wrong probability calculations. Memorize this formula like your favorite song lyric. B minus A plus 1 gives you the count. Now here's a classic MCQ trap. A question will show you random, 0, 9, and ask how many outcomes are possible. Students who aren't careful say 9 because they see the numbers 0 through 9 and forget to count 0 itself. The correct answer is 10 because 9 minus 0 plus 1 equals 10. Zero-based ranges appear constantly in CS contexts, so be especially alert when the lower bound is 0. Calculating probability from random. Once you know how many outcomes exist, probability questions become straightforward. The probability of any single specific value occurring is 1 divided by the total number of outcomes. So for random 1/6, the probability of rolling exactly a 4 is 1/6. For calculating the probability of a range of values, you count how many values in that range fall within the random's output range, then divide by the total outcomes. Let's say you have random 120, and you want to know the probability of getting a value greater than 15. The values that satisfy this are 16, 17, 18, 19, and 20. That's 5 values. Total outcomes are 20. So the probability is 5/20, which simplifies to 1/4 or 25%. On the FRQ, show your counting work clearly. Graders award credit for the reasoning, not just the final fraction. Using random in algorithms, conditionals, and simulation. Random almost never appears in isolation on the AP exam. It shows up inside algorithms, typically paired with conditional statements. A common pattern looks like this. You generate a random number, then use an if statement to take different actions depending on the result. For example, a coin flip simulation might use random 1, 2, where a result of 1 represents heads and 2 represents tails. A traffic light simulation might use random 1, 3 to randomly assign red, yellow, or green. When you see random embedded in a longer code segment on the MCQ section, slow down and trace through every possible path. Ask yourself, what are all the values this could return? Which branch of the conditional does each value trigger? What is the probability of reaching each branch? The exam loves asking you to identify the probability that a particular output or behavior occurs, which requires you to map values to outcomes carefully. Simulation, the big picture connection. This brings us to one of the most important connections you need to make for the exam. Random values are the engine that powers simulations, which is a major concept in Unit 3 and beyond. A simulation uses a computational model to represent a real-world process, and randomness is what allows that simulation to model unpredictable, probabilistic phenomena. Think about weather modeling, epidemiological models that simulate how diseases spread, or Monte Carlo methods used in finance. All of these rely on random number generation. College Board wants you to understand that simulations can be used to explore questions that would be too dangerous, too expensive, or simply impossible to test in the real world. Random values make simulations variable, meaning you can run them many times and observe a distribution of results rather than a single deterministic outcome. This connects directly to the big idea of impacts of computing, where you discuss how simulations serve as powerful tools for scientific discovery and decision-making. Common confusions to clear up right now. 2 things trip students up repeatedly. First, some students confuse random with a procedure that returns a decimal or floating point number. On the AP exam, random always returns an integer, a whole number within the specified range. No fractions, no decimals. Second, students sometimes assume the range has a specific required order, but College Board expects A to be less than or equal to B. You won't see trick questions with random it's 10, 1, but if a range confuses you, just remember, lower bound first, upper bound second. Also worth noting, when the AP exam describes random in a written scenario rather than code, it might describe it in plain English, a random integer from 1 to 6 inclusive. The word inclusive is your cue that you're dealing with the same random behavior and all the same rules apply. Tying it together. Randomness is one of those topics that seems deceptively simple, but rewards careful, precise thinking. Exactly the kind of thinking the AP exam is designed to test. Know the syntax, master the inclusive boundary rule, internalize the counting formula, and practice tracing algorithms that use random inside conditionals, and you'll be in excellent shape. Speaking of algorithms and tracing code carefully, that precision becomes even more important as we move into the world of lists and list operations, where the sequences your programs work with start to get much more interesting and much more powerful. 3.16 Simulations. What is a simulation really? Let's start with a story. Imagine you're an engineer at NASA and you want to test whether a new spacecraft can survive re-entry into Earth's atmosphere. You could, of course, build the spacecraft and send it up, but if your math is off, you lose billions of dollars and potentially lives. Or you could build a simulation, a computer model that mimics the physics of re-entry, runs the experiment thousands of times under different conditions, and tells you what's likely to happen before you ever weld a single panel. That's the power of simulation, and it's exactly what College Board wants you to understand for the AP exam. The College Board defines a simulation as a representation of a real-world or hypothetical situation that uses a computer model to help understand, explore, or test scenarios. Notice 3 things in that definition. It's a representation, not the real thing. It involves a model, an abstraction of reality, and its purpose is to understand or test something. Keep those three ideas close, because exam questions love to probe whether you truly grasp the distinction between the simulation and the phenomenon it represents. Models and abstractions, the foundation. A simulation is only as good as the model underneath it, and every model involves abstraction, the deliberate choice to include certain details and leave others out. Think of a weather forecast app on your phone. The simulation running behind it models air pressure, humidity, temperature gradients, and wind patterns. But it doesn't model every single air molecule. There are roughly 10 so great of them in a room alone. It abstracts away irrelevant detail to make the computation tractable. This connects directly to Unit 2's concept of abstraction, and the connection is intentional. On the AP exam, you will almost certainly see questions that ask you to evaluate whether a simulation is useful given the abstractions it makes. The key insight is that all models are wrong, but some are useful. A simulation that leaves out crucial variables produces unreliable results. A simulation that tries to include everything becomes impossibly complex. Good simulation design is about finding that productive middle ground. When a question asks you whether a simulation accurately models a real-world phenomenon, you need to ask yourself, what has been left out, and does that omission matter for the question being asked? If a traffic simulation ignores weather conditions and you're studying rush hour congestion patterns on a sunny day, the omission might be fine. If you're studying accident rates during winter storms, suddenly, that omission becomes a critical flaw. Randomness and probability. The engine of many simulations. Here's where simulations get genuinely exciting. Many real-world phenomena involve randomness, and simulations can model that randomness using random number generators. You've seen this in everyday life. Your weather app gives you a 70% chance of rain, which comes from a model that has been run thousands of times with slightly varying inputs, and 70% of those runs predicted rain. This technique, running a simulation many times with random variation to estimate a probability or outcome, is called a Monte Carlo simulation. And while the College Board won't use that fancy name on the exam, the underlying idea absolutely shows up. The critical concept here is that more trials generally produce more reliable results. If you flip a virtual coin 10 times in a simulation, you might get 8 heads and 2 tails purely by chance. Flip it 10,000 times, and you'll land very close to 50-50. The exam will test whether you understand that increasing the number of trials in a simulation reduces the effect of random variation and gives you more confidence in the result. This is a common MCQ trap. A question might describe a simulation that was run only a few times and ask whether its results are reliable. The answer is almost always no. Too few trials means the results could easily be anomalies rather than meaningful patterns. What simulations can and cannot do. The College Board draws a careful line between what simulations are good for and where they fall short, and this distinction appears on the exam regularly. Simulations are valuable when the real experiment is too dangerous, too expensive, too time-consuming, or simply impossible. Testing drug interactions before human trials, modeling the long-term effects of climate change, practicing flight maneuvers in a flight simulator. All of these make simulations not just convenient but ethically necessary. However, simulations cannot guarantee real-world accuracy. A simulation is only as reliable as the model it's built on. If your model contains faulty assumptions, your simulation will faithfully reproduce those faulty assumptions at scale. This is sometimes called garbage in, garbage out, and it's a principle you should know cold. A question might describe a simulation that produces surprising or counterintuitive results. Then ask why, and the answer often traces back to a flawed or overly simplified model, not a problem with computers or programming per se. Connecting to the bigger picture. Simulations sit at the crossroads of several AP-CSP concepts. They rely on algorithms, Unit 3, to define the rules of the model. They often use iteration loops that run the simulation repeatedly and conditionals that determine how the simulated system responds to different states. They generate data that must be collected, stored, and analyzed, connecting directly to Unit 5's big data and data analysis concepts. And the question of whether a simulation is ethical, whether it might encode biases, make harmful assumptions, or be used to justify poor decisions, ties directly to Unit 5's computing innovations and social impacts. There's also a subtle but important connection to binary and data representation from Unit 2. All simulations, no matter how sophisticated, reduce the messy analog world to discrete digital values. That translation itself is an act of abstraction, and it means that some precision is always lost. The exam traps you cannot afford to miss. Let me flag 3 traps that show up constantly. First, students confuse the simulation with the thing being simulated. A simulation of a disease outbreak is not a disease outbreak, it's a model, and its conclusions apply to the model, not necessarily to reality. Second, students assume that a simulation that produces consistent results must be accurate. Consistency just means the model is deterministic or well-designed. It says nothing about whether the model reflects reality. Third, students underestimate the importance of identifying what the simulation does not include. Every correct simulation question on the AP exam can be answered by asking, what did we leave out, and does it matter? When you see a simulation question on the free response section, the scoring rubric will reward you for identifying both what the simulation tests and what its limitations are. State them explicitly and connect them back to the concept of abstraction. wrapping up and looking ahead. Simulations are one of the most elegant ideas in all of computer science, using the precision of code to explore worlds that are too big, too dangerous, or too uncertain to explore directly. Master the connection between models, abstraction, randomness, and reliability, and you'll handle every simulation question the AP exam throws at you with confidence. Next up, we'll explore how the internet itself works, which fittingly is a system so vast and complex that engineers use simulations to understand and improve it. 3.17 Algorithmic Efficiency. Let's talk about something that separates good programmers from great ones, and separates students who score a 4 on this exam from students who score a 5. That something is algorithmic efficiency, and once you understand it, you'll never look at code the same way again. Here's a scenario to set the stage. Imagine you're looking for your friend's name in a school directory. If the directory is alphabetical, you flip to the middle, check whether your friend's name comes before or after, and keep having the remaining pages until you find it. But what if the directory wasn't sorted at all? Now you're forced to check every single name, one by one, from the first page to the last. Both approaches find the answer, but one is dramatically faster. That difference in speed, measured in terms of how the number of steps grows as the problem gets bigger, is exactly what algorithmic efficiency is all about. What efficiency really means. The College Board defines algorithmic efficiency as a measure of the number of steps an algorithm requires to solve a problem. Notice what that definition does not say. It doesn't say the fastest code or the fewest lines. It's specifically about how the number of computational steps scales with the size of the input. This is a crucial distinction you need to lock in before exam day. You'll also see the College Board connect efficiency to the concept of reasonable versus unreasonable time. An algorithm that runs in a reasonable amount of time is one where the number of steps grows in proportion to the input size, or perhaps the square of the input size, but stays manageable. An algorithm that runs in an unreasonable amount of time is one where the steps grow exponentially, meaning doubling the input size doesn't double your steps, it squares them, or worse. Picture a chess-playing algorithm that must evaluate every possible sequence of moves. Even for a modest number of turns, the number of possibilities explodes so catastrophically that no computer on Earth could finish it in a human lifetime. That's unreasonable time, and the AP exam will absolutely ask you to classify problems this way. Linear versus polynomial versus exponential growth, the big three. Think of efficiency in 3 broad tiers for this course, and visualize each one on a graph where the horizontal axis is input size, call it n, and the vertical axis is number of steps. In the first tier, linear time algorithms draw a straight diagonal line on that graph, double the input, double the steps. Searching an unsorted list for a specific value is a classic example. You might have to check every element. So if you have 100 names, the search takes 100 steps, and if you have 1,000 names, it takes 1,000 steps. Clean, predictable, and quite manageable. In the second tier, polynomial time algorithms, particularly quadratic ones, draw a curve that bends upward. Think about a simple sorting algorithm that compares each element to every other element. If you have 10 items, you might perform roughly 100 comparisons. If you have 100 items, you might perform roughly 10,000 comparisons. The curve steepens, but it's still workable for reasonably sized inputs. The AP exam considers polynomial time algorithms to run in reasonable time. Now the third tier, exponential time algorithms. On that same graph, this curve doesn't just bend upward, it shoots almost straight up like a rocket. Adding just one more element to your input can double the number of steps required. This is why problems like find the best possible combination of items or try every possible password become computationally intractable very quickly. The AP exam considers these to run in unreasonable time. When you see a problem description where the steps double with each additional input element, that's your signal to classify it as exponential. Here's the graph you should be able to sketch and label. Draw 2 axes, label the horizontal axis input size n, and the vertical axis number of steps. Draw 3 curves, a straight line for linear growth, a gentle upward curve for polynomial quadratic growth, and a dramatically steep curve for exponential growth. Know which curve belongs to which category, because the AP exam has absolutely shown students a graph and asked them to identify the type of growth. The heuristic approach, when perfect, isn't possible. Here's something the College Board specifically wants you to understand. When a problem can't be solved in reasonable time, programmers often turn to heuristic approaches. A heuristic is a problem-solving strategy that finds a solution that is good enough, even if it isn't guaranteed to be the optimal or perfect solution. Think of a GPS that calculates a very good route in seconds, rather than spending hours evaluating every possible path in a city. It might not find the absolute fastest route in every single case, but it finds a very good one quickly. That trade-off, accuracy for speed, is the defining feature of a heuristic. On the exam, if you see a question asking what technique a programmer might use when an exact solution is computationally impractical, the answer is almost certainly heuristic. Common exam traps and how to dodge them. The most common trap on this topic is conflating correctness with efficiency. 2 algorithms can produce identical correct outputs while differing enormously in efficiency. The exam will show you 2 algorithms that both solve the same problem and ask which is more efficient. Don't get distracted by whether they work. Focus on how many steps each one takes as the input grows. A second trap involves the phrase always finds the best solution. A heuristic does not always find the best solution. That's literally the definition. If an answer choice says a heuristic guarantees an optimal result, it's wrong. A third trap involves confusing what the algorithm does with how long it takes to do it. An exponential time algorithm isn't broken or incorrect, it's just slow at scale. Don't assume inefficiency means incorrectness. Connections across the course. This topic weaves tightly into your work in Unit 2 when you studied binary search versus linear search. Binary search is dramatically more efficient because it eliminates half the possibilities with each step. It also connects to the big idea of computing innovations in Unit 5, where processing enormous datasets, think social media platforms, analyzing billions of posts, requires efficiency to even be possible. The concept of undecidable problems later in the course is the ultimate example of unreasonable time. Some problems aren't just slow to solve, they literally cannot be solved by any algorithm at all. Understanding how efficiency shapes what computers can and cannot accomplish in practice is one of the most powerful ideas in all of computer science, and it's going to show up on your exam in ways both direct and subtle. Keep that graph in your head, know your 3 growth types cold, and remember what a heuristic trades away in exchange for speed. With efficiency under your belt, you're ready to move into the territory of undecidable problems, where we'll discover that some questions are so complex, no algorithm, no matter how efficient, can ever answer them. 3.18 Undecidable Problems. The question that broke mathematics. Let's start with a thought experiment. Imagine you write a program and ask a computer scientist to look at it. You want to know one simple thing. Will this program ever finish running, or will it loop forever? Seems like a reasonable question, right? Here's the jaw-dropping truth that shook the entire field of computer science in the 20th century. No algorithm can ever answer that question perfectly for every possible program. Not a faster computer, not a smarter programmer, not 1,000 years of trying. It is mathematically provably impossible. That's the world of undecidable problems, and understanding it is your key to conquering this section of the AP exam. Decidable versus undecidable. Getting the definitions right. The College Board wants you to know these terms with precision, so let's nail them down. A decidable problem is one where an algorithm can always be written to produce a correct yes or no answer in a finite amount of time for every possible input. Notice that phrase, every possible input. That's the standard. A decidable problem always terminates with the right answer, no exceptions. Classic examples include, is this number even? Or, does this list contain the value 7? You can write clean, reliable algorithms for these all day long. An undecidable problem, on the other hand, is one where no algorithm can ever exist. Not just one that hasn't been found yet, but one that cannot exist, that always gives a correct yes or no answer for all possible inputs. The problem isn't that we're not clever enough. The problem is that the universe of mathematics won't allow it. This distinction is enormous for the exam. The halting problem, your most important example. The canonical undecidable problem you absolutely must know for the AP exam is the halting problem. It asks, given a program and its input, can you determine whether that program will eventually stop, halt, or run forever? Alan Turing, the brilliant British mathematician often called the father of computer science, proved in 1936 that you cannot write a general algorithm to solve this for all programs. Here's an analogy that makes this click. Imagine you're watching someone read a book. Will they finish it or read forever? You might say, just watch them. But what if the book had rules that said go back to chapter 1 whenever you reach the end? And what if those rules changed based on what they'd already read? To know if they'll ever stop, you essentially have to read the book for them, but that could take infinite time. You can't peek ahead reliably. Programs are like that, only infinitely more complex. The key College Board takeaway, the halting problem is undecidable, meaning there is no algorithm that correctly solves it for every program. This does not mean computers are useless. It means there exists a specific category of question that sits permanently outside the reach of algorithmic solutions. What undecidable does not mean the biggest exam trap. Here's where students lose points, and this is the trap you will not fall into. Undecidable does not mean a problem is hard, slow, or unsolvable for specific cases. You might absolutely be able to write a program that correctly determines whether some programs will halt, maybe even most of them. The problem is you can never write one that works for all inputs without sometimes being wrong or running forever itself. The impossibility is about generality and completeness, not difficulty. Another trap. Students sometimes confuse undecidable problems with problems that are merely computationally expensive or that run into resource limitations. Those are a different beast entirely. They're about efficiency, and they live in the territory of algorithms and optimization, not mathematical impossibility. If a problem takes 1,000,000 years but theoretically terminates with the right answer, it's still decidable. Undecidable means the wall is made of logic itself, not time or hardware. The some instances can be solved nuance. The AP exam loves to test this nuance. Just because a problem is undecidable in general doesn't mean every specific instance is unsolvable. You might write a program that looks at a particular piece of code and correctly says, this one will halt, and you'd be right. The problem is that your program will fail or loop forever on at least some other input. A perfect general solution is impossible, but partial solutions absolutely exist. This is an edge case that appears regularly on multiple choice questions, so train yourself to catch it. The question will often describe an algorithm that works most of the time and ask whether that makes the problem decidable. The answer is no. Decidability requires working correctly for all inputs. Connecting this to the rest of the course, undecidable problems connect directly to several other areas you've studied. Think back to your work on algorithms and efficiency in Unit 3. You learned that some problems can be solved, but are just slow, like those requiring exponential time. Undecidable problems are a step beyond even that. They aren't in the category of hard to solve, but rather impossible to solve with any algorithm ever. They represent the outer boundary of what computation can do. This topic also connects to the broader theme of limits of computing that runs through Unit 3. The College Board wants you to appreciate that computers are extraordinarily powerful tools, but they exist within mathematical constraints. The halting problem is the most elegant proof of that constraint. It also touches on the idea that as problems scale, their behavior can become unpredictable, a theme you'll recognize from discussions of large datasets and algorithmic complexity. What to remember when you sit down for the exam. When the AP exam presents you with a scenario about undecidable problems, anchor yourself to 3 things. First, the halting problem is your gold standard example of an undecidable problem. Know it cold. Second, undecidable means no algorithm exists that is always correct for all inputs, not that the problem is merely difficult. Third, some instances of an undecidable problem can be solved. This doesn't make the problem decidable. If you see a question asking whether a given problem is decidable, ask yourself, can I imagine writing an algorithm that always gives the right yes or no answer, terminates in finite time, and handles every conceivable input? If the answer is yes, decidable, if there's any scenario where the algorithm would fail or run forever, you're in undecidable territory. The beauty of this topic is that it invites you to think like a computer scientist at the deepest level, not just coding solutions, but understanding what solutions are even possible. As we move forward into exploring how these ideas interact with real-world problem solving and the ethical dimensions of what computing can and cannot do, you'll find that this theoretical foundation makes everything else sharper and clearer. 3.19 Nested Loops and Loop Behavior. Generation failed. 3. Tracing code and predicting output. Let's talk about one of the most powerful skills you'll use on the AP CSP exam, and honestly, one of the most useful skills in all of programming. Tracing code and predicting output. Think of it like being a detective. The code is your crime scene, and your job is to follow every clue, every variable, every loop, every conditional until you can say with confidence, here's exactly what happens when this program runs. Master this skill, and a huge portion of the AP exam becomes manageable in a way it simply isn't for students who skip it. What tracing actually means. Tracing code means manually stepping through a program, line by line, tracking the exact state of every variable at every moment. Imagine you're a very literal-minded robot. You don't assume anything, you don't skip ahead, you do exactly what each line says in order, and you keep a mental or physical notebook of what every variable holds at each step. That notebook is called a trace table, and drawing one is your single best friend on the AP exam. A trace table typically has columns for each variable in the program and rows for each step or iteration. Every time a variable changes, you update its cell. When the code finishes, your last row tells you exactly what gets displayed or returned. Variables and assignment. The foundation before you can trace anything, you need to be rock solid on assignment. In AP pseudocode, x5 means x now holds the value 5. It does not mean x equals 5 forever. It means x holds 5 right now until something changes it. This trips up so many students who come from a math background where x equals 5 is a permanent truth. In programming, xx plus 1 is perfectly legal and just means take whatever x currently holds, add 1, and store the result back into x. If x was 5, now it's 6. Write that in your trace table and keep moving. A common MCQ trap involves reading an assignment backwards. When you see A, B, it's B going into A, not the other way around. The value on the right replaces whatever is on the left. If B is 10 and A is 3, after this line it becomes 10 and B stays 10. Students who misread direction here will pick the wrong answer every single time. Tracing conditionals. Conditionals are the fork-in-the-road moments of a program. When you hit an if statement, your job as a tracer is to evaluate the condition using the current values in your trace table, not what they were a few lines ago, not what you think they'll be later. If the condition is true, you follow that branch. If false, you skip to the else or move past the entire block. On the AP exam, watch out for nested conditionals, where one if lives inside another. Trace them the same way, just one layer at a time. The outer condition gets evaluated first, and only if it's true do you even look at the inner one. Tracing loops where the magic and madness happen. Loops are where most tracing errors happen, and they're also where the AP exam loves to test you. A repeat n times loop runs its body exactly n times, Count them on your fingers if you have to. A repeat until loop keeps running until its condition becomes true. Notice that phrasing carefully. It stops when the condition is true, not when it's false. Students constantly mix this up with a while loop, which continues as long as the condition is true. These are opposite behaviors, and the AP exam absolutely exploits this distinction. When tracing a loop, extend your trace table downward for each iteration. Label each pass, iteration 1, iteration 2, and so on. Track every variable that changes during the loop body. A classic MCQ will show you a loop that runs 5 times and ask for the final value of a variable. Students who don't trace carefully will often be off by 1, counting 4 iterations instead of 5, or 5 instead of 6. This off by 1 error is one of the most reliable MCQ traps on the entire exam. To avoid it, always note explicitly when the loop starts and what condition causes it to end, then count iterations methodically. Consider a loop where count starts at 1 and you repeat until count greater than 5, incrementing count by 1 each time. The loop runs when count is 1, 2, 3, 4, and 5. That's 5 iterations. The moment count becomes 6, the condition count at greater than 5 is finally true, and the loop exits with count holding 6. Students who say the answer is 5 have fallen into the trap of thinking the loop stops at 5 rather than after checking 5. Lists and index tracing. When code involves lists, your trace table needs a column for the list itself, or at least for the index variable and the list element being accessed. In AP pseudocode, lists are one indexed, meaning the first element is at index 1, not 0. This is a crucial difference from many real-world programming languages like Python or JavaScript, and it generates wrong answers on the exam for students who bring outside habits into AP pseudocode. When you see MyList, you're accessing the element at position I, and if the loop runs I from 1 to length MyList, you're hitting every element exactly once. Procedures and return values. When a procedure is called, trace into it. Substitute the actual argument values for the parameter names, trace the procedure body, and if there's a return statement, bring that value back to wherever the call happened. The outer code then continues with that returned value in hand on the FRQ, showing your trace clearly, labeling parameter substitution, showing each step inside the procedure, is exactly what earns partial credit, even if your final answer is wrong. Connecting to the bigger picture. Tracing connects to virtually every other programming topic in Unit 3 and beyond. When you study searching and sorting in later sections, you'll trace those algorithms to prove you understand how they work. When you analyze correctness in Section 3.9, you're essentially asking, does tracing this code produce the intended output for all inputs? And when the exam gives you an algorithm and asks whether it produces correct results, your tool is always the trace table. Think of tracing as the universal translator of computer science. It converts any abstract code into concrete, checkable behavior. Build the habit now of slowing down, writing out your trace table, and never skipping steps. And you'll be amazed how many hard questions become completely straightforward. With a solid foundation in tracing, you're perfectly positioned to tackle the next challenge, understanding how algorithms can be designed and evaluated for efficiency, which is exactly where we're headed next. 3.21 Parameters and return values. The vending machine model. Let's start with the vending machine, because honestly, it's the perfect mental model for this entire topic. You walk up, you press B7, you get a bag of chips. You provided an input, the machine did some internal processing, and you got an output back. That's exactly what parameters and return values are all about. Parameters are the inputs you hand to a procedure, and return values are what the procedure hands back to you. Simple concept, enormous power, and the AP exam absolutely loves testing whether you truly understand the difference between the two. Here's the College Board's official language, and you need to know it cold. A parameter is a variable in the definition of a procedure that receives the value of an argument when the procedure is called. And the argument is the actual value you pass in when you make that call. Students confuse these two words constantly, and the exam will absolutely exploit that confusion. Think of it this way. The parameter is the label on the slot in the vending machine, B7, and the argument is the actual button you press, you physically pressing B7. The slot exists in the machine's design. The button press happens in the real world. How parameters work in pseudocode. On the AP exam, you'll see procedures written in the College Board's pseudocode format. A procedure definition looks like this. Procedure make sandwich, bread, filling. Here, bread and filling are the parameters. They're placeholders, like variables waiting to be given a real value. When you call that procedure later with make sandwich sourdough, turkey, you're passing arguments. The parameter bread takes on the value sourdough inside that procedure, and filling takes on turkey. The procedure uses those values to do its work. This matters deeply because procedures with parameters are reusable. Instead of writing separate procedures for a turkey sandwich, a ham sandwich, and a cheese sandwich, you write one procedure and change the argument each time you call it. That's the entire power here. Abstraction through generalization, and the exam absolutely tests this idea. If you see a question asking why you would use a parameter instead of just hard coding a value inside the procedure, the answer is always about reusability and flexibility. Return values, getting something back. Now let's talk about the other half of this topic. Some procedures just do things. They print something to the screen, they move a robot, they change a value somewhere. Those don't need to return anything. But other procedures calculate something and need to hand that result back to whoever called them. That's where the return statement comes in. In College Board pseudocode, a procedure that sends a value back uses return expression. For example, imagine a procedure procedure double x that contains return of x to 2. When you write result double 5 in your program, the variable result gets the value 10. The procedure ran, did its math, and handed 10 back. Your program grabbed it and stored it. Here's a critical exam trap. If a procedure has a return statement, you need to capture that return value by assigning it to something or using it in an expression. If you call double 5 but don't assign the result anywhere, that 10 just evaporates into the void. The exam loves asking questions where a student calls a procedure but forgets to use the returned value, leading to a variable staying at its old value instead of updating. Watch for that. Scope, the hidden layer. Here's a concept that lives right underneath parameters and return values, but is crucial for the exam. Scope, variables defined inside a procedure, including the parameters themselves, are local to that procedure. They exist only while the procedure is running, and they're invisible to code outside that procedure. This is why you can have a variable named X inside one procedure and a completely different variable named X in another procedure, and they never interfere with each other. The real-world analogy here is a conversation. When your friend tells you a secret, that secret lives in your conversation. It doesn't automatically travel to everyone else in the building. Variables inside a procedure stay inside that conversation. The exam trap with scope goes like this. A question shows a procedure that modifies a variable and then asks what value that variable has outside the procedure. If the variable was defined inside the procedure, the answer is that the outside code has no access to it at all. Any change made inside doesn't affect the outer variable unless you use a return statement to explicitly send that value out. The difference between displaying and returning. This is one of the most commonly missed distinctions on the entire exam. A procedure that uses dispel of X shows something on screen. A procedure that uses return X sends a value back to the calling code. These are not the same thing. A student might see a procedure that displays a result and assume the program can use that displayed value somewhere else. It cannot. Dispel is output for humans to read. Return is output for your program to use. Exam questions will absolutely present both in similar-looking code and ask you to trace what value a variable holds. If the procedure only displays and never returns, the calling code gets nothing back, and any variable you tried to assign the call to will remain unchanged or undefined. Connections across the course. This topic threads through almost everything else in Unit 3 and beyond. When you get to 3.3 on mathematical expressions, you're often computing values you'll want to return from a procedure. In 3.12 and 3 on calling procedures and developing them, parameters and return values are the backbone of how those procedures interact with each other. When the course later touches on lists and iteration, you'll frequently write procedures that take a list as a parameter and return a modified version or a computed result from that list. And in the Create Performance task, the actual AP project you submit, clear use of parameters and return values is one of the things scored on your written response. The exam rubric specifically looks for whether your procedure takes at least one parameter that influences its behavior. If your procedure doesn't use its parameters in a meaningful way, you're leaving points on the table. The big picture takeaway is this. Parameters let you feed information into a procedure and return values let you bring results out. Together, they transform a procedure from a static set of instructions into a flexible, reusable tool. And that's exactly the kind of abstraction the AP exam rewards you for understanding deeply. With parameters and return values firmly in hand, you're ready to zoom out and see how all these individual procedures fit together into larger, more complex programs, which is exactly where we're headed next. 3.22 Recursive Thinking, Conceptual. Let's talk about one of the most mind-bending, elegant ideas in all of computer science, recursion. And I want to start with a story. Imagine you're standing between two mirrors facing each other. You look into one mirror and see a reflection of yourself, but inside that reflection is another reflection, and inside that one is yet another, stretching off into what feels like infinity. That image, a thing defined in terms of itself, is the heart of what recursive thinking is all about. What recursion actually means. Recursion, in the context of AP computer science principles, is the practice of a process calling itself as part of its own definition or solution. The College Board defines a recursive algorithm as one that calls itself, where a recursive call is part of the algorithm. This sounds circular at first, and you might ask, doesn't that just go on forever? That's exactly the right question, and the answer brings us to the two most critical components of any recursive process, the base case and the recursive case. The base case is the condition under which the recursion stops. It's the mirror finally hitting a wall. There's no more reflection to create. Without a base case, you'd have infinite recursion, which in a real program causes something called a stack overflow. The recursive case is every situation that is not the base case. It's where the function calls itself with a smaller or simpler version of the original problem. Every time a recursive call is made, the problem should be getting smaller, nudging closer and closer to that base case. Think of it like nesting dolls, a matryoshka. You open the biggest doll, and inside is a slightly smaller one. You open that one, and there's an even smaller one. Eventually, you reach the tiniest doll that doesn't open. That final solid doll, that's your base case. A concrete example, counting down. Let's make this tangible. Imagine a recursive process that counts down from a number to 0. Here's how the logic flows. If the number is 0, print done and stop. That's the base case. If the number is greater than 0, print the number and then repeat the whole process with the number -1. That's the recursive case. So counting down from 3 looks like this. You start with 3, call the process with 2, then with 1, then with 0. And at 0, you finally stop. Each call is working with a simpler version of the original problem. This brings up a critical concept the AP exam loves to test. Each recursive call must make progress toward the base case. If you called the process with the same value each time or a larger value, you'd loop forever. That's an edge case that shows up in multiple choice questions disguised as a small subtle change to the recursive rule. Watch out for those. Why recursion matters. The power of self-reference. Here's why computer scientists love recursion. It lets you express solutions to complex problems with beautiful simplicity. Some problems have a structure that is naturally self-similar. Think about searching through folders on your computer. A folder can contain files and other folders. To search through everything, you look at each file, and whenever you find a folder, you search through that folder using the exact same process. That's recursion happening in the real world right now. Every time your computer searches for a file. Another classic example is the Fibonacci sequence, where each number is the sum of the two numbers before it. The sequence goes 0, 1, 1, 2, 3, 5, 8, 13, and so on. A recursive definition fits perfectly. The Fibonacci value of n is the Fibonacci value of n-1 plus the Fibonacci value of n-2 times, with base cases at 0 and 1. Notice there are two base cases here. This is something the exam will test. A recursive algorithm can have more than one base case, and you need to handle all of them, or the recursion won't stop correctly. Recursion versus iteration, a key distinction. The AP exam will absolutely test your ability to distinguish between recursive and iterative solutions. An iterative solution uses loops, repeating a block of code a set number of times. A recursive solution repeats by calling itself. The College Board wants you to know that any recursive solution can be rewritten as an iterative one, and vice versa. They are equally powerful in terms of what problems they can solve. The difference is often one of clarity and elegance. Some problems, like the folder search or Fibonacci, feel natural in recursion. Others feel more natural with a simple loop. A common MCQ trap is showing you a recursive procedure and asking what it would output, then including answer choices that reflect what a loop version might do incorrectly. Work through recursive problems step by step, checking each call and its return value. Don't try to hold the whole thing in your head at once. Think one level at a time. Tracing through recursion, your exam strategy. When the exam gives you a recursive algorithm and asks you to trace it, here's the strategy. Start at the first call. Identify whether the input is the base case or not, and if not, write down the recursive call you're about to make. Keep doing this, step by step, until you hit a base case. Then work backwards, substituting return values back up the chain. This unwinding process is where students most commonly make mistakes. They get to the base case and forget that the program still has to finish all those other calls that were waiting. Another trap to watch for, confusing the order in which things print or execute. If a recursive call happens before a print statement, you'll see output in reverse order compared to if the print happens first. The exam loves to swap these and see if you notice. Connections to other units. Recursive thinking connects directly to your work with algorithms throughout Unit 3, particularly when you're analyzing algorithm efficiency and comparing approaches to solving the same problem. It also connects to Unit 4, where you'll think about how algorithms handle large datasets and the idea that some recursive algorithms can be inefficient because they repeat the same calculations many times. Fibonacci is a perfect example. Computing Fibonacci of 5 means computing Fibonacci of 3 and 4, but computing Fibonacci of 4 also requires Fibonacci of 3, so you do the work twice. Understanding this redundancy is a gateway to understanding why algorithm efficiency matters at scale. Recursive thinking is one of those concepts that once it clicks, you start seeing it everywhere, in the structure of the internet, in sorting algorithms, in how your phone organizes photos. It's a fundamental way that programmers decompose complex problems into manageable pieces, and mastering it conceptually puts you in excellent shape for both the multiple choice and the written portions of your AP exam. Now that you've got recursion in your toolkit, let's turn to how we evaluate and compare algorithms more formally, because once you can write a solution, the next question is always, how efficient is it? 3.23. Searching algorithms, linear search versus binary search. Setting the stage, why searching matters. Imagine you're at a massive library with 10,000 books, and someone asks you to find a specific title. How you approach that search makes all the difference in the world, and that's exactly what this section is about. Searching algorithms are among the most fundamental tools in computer science, and the AP exam will absolutely test whether you understand not just how they work, but when to use each one and why one is faster than the other. Let's dig in. Linear search, the honest, hard-working approach. Linear search is the algorithm you already use intuitively, even if you've never written a line of code. Think about searching for a friend's name in an unsorted stack of index cards. You pick up the first card, check it, set it aside if it's not right, and move to the next. You keep going until you either find what you're looking for or run out of cards. That's linear search, also called sequential search in a nutshell, in code terms. Linear search starts at the first element of a list and checks each element one by one in order until it finds the target value or reaches the end of the list without finding it. The critical thing to internalize here is that linear search works on any list, sorted or unsorted. That flexibility is its great strength. Now let's talk efficiency. In the best case, the element you're looking for is the very first one. You find it immediately. In the worst case, the element is last on the list, or it isn't there at all, and you have to check every single element before you know that. For a list of n elements, the worst case requires n comparisons. Computer scientists describe this as ON linear time, which the AP exam doesn't require you to write in big O notation, but the concept is fair game. The College Board phrases it like this: the number of steps grows in direct proportion to the number of elements. If your list doubles in size, your worst case search time also doubles. Keep that proportional relationship locked in your memory. Binary search, the elegant shortcut. Now picture this. Instead of a random pile of index cards, your library has its books arranged in perfect alphabetical order. You don't start at A and read every spine. You open to the middle of the library. See, you're in the M section, and your target is F, so you immediately ignore everything from M onward and focus only on the first half. Then you find the middle of that section, check again, and keep cutting your search space in half. This is binary search, and it's beautifully efficient. Here's the rule you absolutely must memorize for the AP exam. Binary search only works on a sorted list. This is the single biggest trap on multiple choice questions. If a list is not sorted, you cannot use binary search, period. The College Board loves to give you an unsorted list and ask which algorithm can be used. Linear search is always valid, but binary search requires sorting first. The process works like this. You examine the middle element of the list. If it matches your target, you're done. If the target is less than the middle element, you eliminate the entire upper half and search only the lower half. If the target is greater, you eliminate the lower half and search only the upper half. You repeat this process on the remaining portion, each time cutting the search space in half. This leads to the efficiency formula the AP exam wants you to understand. For a list of n elements, binary search takes at most log base 2 of n steps to find a result, or confirm the element isn't there. The College Board doesn't ask you to compute logarithms, but they absolutely want you to understand the proportional relationship. If your list has 8 elements, binary search needs at most 3 steps. A list of 16 elements needs at most 4 steps. A list of 1024 elements, just 10 steps. You can see how dramatic this is. Doubling the list size only adds 1 step. That's the power of binary search. If you're ever asked to visualize this, picture a simple table. On one side, the number of elements, 1, 2, 4, 8, 16, 32, 64, 128, 10,024. On the other, the maximum number of steps for binary search, 0, 1, 2, 3, 4, 5, 6, 7, 10. Each time the left column doubles, the right column increases by just 1. Meanwhile, linear search's steps increase in lockstep with the list size. That visual comparison is exactly the kind of thing the AP exam will ask you to interpret. Edge cases and exam traps to watch for. Let's talk about the situations that trip students up on test day. First, when a list has only one element, both algorithms find it, or don't, in one step. That's a boundary condition worth noting. Second, when the target is not in the list at all, linear search must check every element before concluding the target is absent. Binary search also exhausts its halving process and concludes absence when the search space is empty. This is called an unsuccessful search, and both algorithms handle it, just with very different numbers of steps. A classic wrong answer trap goes like this. The exam describes a sorted list of 1,000 elements and asks which algorithm is more efficient. Students sometimes say it depends, but here it doesn't. For large sorted lists, binary search is always more efficient in the worst case. Another trap? The exam might ask whether binary search can be applied after sorting a previously unsorted list. The answer is yes, you sort it first, then apply binary search. But the sorting step itself takes time, so if you only need to search once, it might not be worth sorting first. That nuance has appeared on free response question. Connections to the rest of the course. This topic connects directly to Unit 3's broader discussion of algorithm efficiency, which you'll revisit when studying sorting algorithms. It also connects to the concept of traversing lists, which you explored when learning about iteration and loops. Linear search is essentially a loop that traverses a list. When the exam asks you to trace through code, you may need to identify whether a given loop implements a linear search. Binary search also connects to the idea of iteration and conditionals working together, since each step requires a comparison that determines which half to keep. On the create performance task, if you build a program that searches through data, you'll want to speak intelligently about your algorithm choice and its efficiency. That's exactly the kind of design decision the AP exam rewards. Wrapping up. Linear search is your dependable workhorse, flexible and always correct, but slower on large datasets. Binary search is your precision instrument, blazingly fast, but only available when the list is sorted. Knowing which to use and being able to explain why is the mark of a student ready to score a 5. With searching algorithms firmly in hand, you're ready to tackle the next piece of the puzzle, sorting algorithms, where you'll discover how computers bring order to chaos and what it costs them to do it. 3.24 Sorting Algorithms, Conceptual Understanding. Let's talk about sorting, and I don't mean organizing your sock drawer, though honestly, that analogy is going to come in handy in about 2 minutes. Sorting algorithms are one of the most beautifully practical ideas in all of computer science, and the AP exam wants you to understand 2 of them deeply: selection sort and insertion sort. You don't need to write them from scratch on the exam, but you absolutely need to understand how they work, why they matter, and crucially, how efficient they are. Let's dig in. What is sorting and why does it matter? Imagine you have a stack of 2,000 student exams you need to arrange alphabetically. You could grab them randomly and keep reshuffling until they're in order technically possible, but catastrophically slow. Or you could use a systematic strategy. That's exactly what sorting algorithms do. They give a computer a repeatable, logical procedure for arranging data in order. The AP exam uses sorting as its central example of how algorithm design directly affects efficiency. And efficiency connects directly back to Unit 3's bigger theme, that the way you solve a problem matters just as much as that you solve it. Sorting also connects to search. Remember binary search from earlier in this unit? Binary search only works on data that's already sorted. So sorting isn't just a standalone skill, it's the foundation that makes faster searching possible. Keep that relationship in your back pocket because the exam loves to ask about it. Selection sort. Finding the minimum again and again. Let's start with selection sort, because it's the one that feels most intuitive. Picture those 2,000 exams again, spread out on a giant table. Here's the strategy. Scan the entire pile, find the exam that comes first alphabetically and pull it out, then scan what's left, find the next one, pull it out. Repeat until you're done. That's selection sort. More precisely, selection sort works by dividing the list into 2 parts, a sorted portion on the left and an unsorted portion on the right. At each step, the algorithm finds the minimum value in the unsorted portion and swaps it into its correct position at the boundary between the 2 portions. Then the boundary moves 1 step to the right, the sorted portion grows by 1, and you repeat. Here's what this looks like in practice. Say you have the list 5, 3, 8, 1, 4. On the first pass, you scan all 5 elements, find that 1 is the smallest, and swap it with the 5 at the front. Now your list is 1, 3, 8, 5, 4. The sorted portion is just the number 1. On the second pass, you scan the remaining 4 elements, find 3 is already in position, swap nothing, and advance the boundary. You continue like this until the entire list is sorted. The AP exam key insight about selection sort is this. It always makes the same number of comparisons regardless of the input. Whether the list is already sorted or completely backward, selection sort still scans the whole unsorted portion every single time. This makes it what we call a quadratic algorithm, meaning its efficiency is proportional to n squared, where n is the number of elements. For the exam, you don't need to calculate exact runtimes, but you do need to know that selection sort is considered less efficient on large datasets, and that its performance doesn't improve just because the data is already partially sorted. Insertion sort, building order 1 card at a time. Now let's talk about insertion sort, and here the analogy shifts from a table to a card game. Think about picking up cards 1 at a time in a hand of poker. Each time you draw a new card, you slide it into its correct position among the cards you're already holding. You don't resort your entire hand from scratch, you just find where the new card belongs and insert it. That's insertion sort. The algorithm maintains the sorted portion at the front of the list, but it builds it differently than selection sort. Instead of hunting for the global minimum, insertion sort takes the next element in the unsorted portion and inserts it into the correct position within the sorted portion by comparing it backward through the sorted section until it finds its home. Using the same example, 5, 3, 8, 1, 4, insertion sort begins by treating 5 as a sorted list of 1. Then it takes 3, compares it to 5, sees that 3 is smaller, and shifts 5 right to insert 3 at the front. 3, 5. Then it takes 8, compares it to 5, sees 8 is larger, and places it at the end. 3, 5, 8. Then it takes 1, compares backward through 8, 5, and 3, shifts all of them right, and inserts 1 at the front. 1, 3, 5, 8, and so on. Here's the critical exam distinction. Insertion sort is actually more efficient than selection sort when the list is already mostly sorted. If the data is nearly in order, insertion sort does very few comparisons and almost no shifting. In the best case, a perfectly sorted list. Insertion sort is linear, meaning it runs in n steps rather than n squared. The AP exam will test whether you understand this nuance. If a question gives you a scenario with nearly sorted data and asks which algorithm would be faster in practice, the answer is insertion sort. The big picture. Efficiency and algorithm design. Both selection sort and insertion sort are what the College Board calls less efficient sorting algorithms, especially on large datasets. There are faster algorithms like merge sort that perform significantly better, and Unit 3 wants you to appreciate why efficiency matters. Running a quadratic algorithm on a list of 1,000,000 elements versus a more efficient one isn't just a small difference. It's the difference between an answer appearing instantly and your program running for hours. A classic MCQ trap here is assuming that a shorter or simpler looking algorithm is automatically more efficient. Selection sort and insertion sort look elegant and readable, but that simplicity comes at a cost on large inputs. Don't confuse readability with efficiency. Another trap, students often think that insertion sort and selection sort are interchangeable in all situations. Remember that selection sort's performance is consistent regardless of input order, while insertion sort's performance varies based on how sorted the data already is. Those are fundamentally different behavioral profiles, and the exam tests that distinction directly. When drawing or describing these algorithms on an FRQ or written response, always identify the sorted and unsorted portions explicitly, trace through at least a few steps with a concrete example, and note what comparison or swap is happening at each step. Examiners want to see that you understand the process, not just the outcome. Connections to the rest of the course. Sorting ties back to Unit 3's concept of algorithm efficiency and connects forward to Unit 4's discussion of how data is stored and accessed. It also reinforces the idea from Unit 3 that all algorithms can be evaluated not just for correctness, but for how well they scale. Every time you see a question about why we choose one approach over another, sorting is the perfect lens through which to think about that trade-off. With sorting algorithms now sorted out, pun absolutely intended, you're ready to explore how we formally measure and compare the efficiency of different algorithms, which is exactly where we're headed next. 3.25 Heuristics and Approximate Solutions. What is a heuristic? Anyway, picture this. You're trying to find the best possible route to drive across the entire country, hitting 15 different cities. Sure, in theory, you could calculate every single possible route, but there are so many combinations that even a supercomputer would be grinding through that problem long after you've retired. This is the world where heuristics live, and understanding them could be worth serious points on your AP exam. A heuristic is a problem-solving approach that finds a good enough solution when finding the perfect solution would take too long or use too many resources. The College Board defines it precisely. A heuristic is an approach to a problem that produces a solution that is not guaranteed to be optimal, correct, or complete, but is sufficient for the immediate goals. That phrase, not guaranteed to be optimal, is going to show up in your exam, so make sure it's burned into your memory. Think of a heuristic like asking a local for directions instead of calculating the mathematically shortest path. The local's directions might not be the absolute fastest, but they'll get you there, and they took about 5 seconds to give. That trade-off between speed and perfection is the entire heart of this topic. Why heuristics exist, the problem of intractability. To really understand why heuristics matter, you need to connect this concept back to what you learned about algorithm efficiency and computational complexity. Some problems scale reasonably. If you double your input, your algorithm takes roughly twice as long, or maybe 4 times as long. Those are manageable. But certain problems are what computer scientists call intractable. As the input size grows, the time required to solve them exactly grows so fast, think exponential or factorial growth, that no realistic amount of computing power can handle large inputs in any reasonable time frame. The traveling salesman problem, which asks for the shortest route visiting every city exactly once, is the classic example you might see on your exam. With 4 cities, there are only 6 possible routes. With 10 cities, there are over 180,000. With 20 cities, more than a quintillion. Exact solutions become impossible at scale, and this is exactly the scenario where heuristics step in to save the day. How heuristics work in practice. When a program uses a heuristic approach, it's essentially making educated guesses and following practical rules of thumb to narrow down the solution space dramatically. Instead of checking every possibility, it prioritizes promising paths. The solution it finds is approximate, meaning it's close to correct or close to optimal, but you cannot guarantee it's the best possible answer. A wonderful everyday analogy. Imagine you're searching for your lost keys. An exhaustive algorithm would check every square inch of your house in a perfectly systematic order, a heuristic says. I usually put my keys near the door, let me check there first. You might not always be right, but you'll find them faster almost every time. The heuristic uses prior knowledge and reasonable assumptions to skip work that probably won't pay off. On the AP exam, you need to be able to identify when a problem benefits from a heuristic approach, describe what makes an approach heuristic rather than exact, and explain the trade-offs involved. The core trade-off, speed versus optimality, the most important conceptual point for your exam, and the most common trap in multiple-choice questions, is understanding the fundamental trade-off a heuristic makes. You gain speed and feasibility, and you give up the guarantee of a perfect answer. Students often write on the exam that heuristics always find a good solution, or that they usually find the optimal solution. Both statements are too strong. The correct framing, in College Board language, is that heuristics find solutions that are good enough for practical purposes, in a reasonable amount of time, even though those solutions may not be optimal. A heuristic could theoretically find the best solution on some runs. It's just not guaranteed to do so every time. Another trap: some students think heuristics are only used when the exact solution is impossible to compute at all. That's not quite right either. Even when an exact solution is theoretically computable, it might take so long that it's practically useless, and that's equally valid justification for a heuristic. If your spam filter had to run for 6 hours to sort your emails, it wouldn't matter how accurate it was. Real-world applications you should know. The AP exam loves connecting concepts to real-world technology, so let's talk about where you actually see heuristics in action. GPS navigation apps don't compute the single globally perfect route. They use heuristic pathfinding algorithms like a star that find excellent routes in milliseconds. Spam filters use heuristic rules to classify email without needing to perfectly understand every message. Video game AI uses heuristics so that characters make reasonable decisions without grinding the processor to a halt. Medical diagnosis software uses heuristic reasoning to suggest probable conditions based on symptoms. Each of these examples involves the same pattern: a problem too complex for a perfect, exhaustive solution, a heuristic approach that gives a result good enough to be useful, and a trade-off where you accept some chance of imperfection in exchange for practical speed. Connecting to undecidable problems. Here's where this topic links beautifully to another area you'll study: the concept of problems that cannot be solved algorithmically at all, known as undecidable problems. The halting problem is the famous example. No algorithm can always determine whether any given program will eventually stop or run forever. Heuristics can sometimes give you useful partial answers even for undecidable problems, but you must understand that they still cannot guarantee correctness in those cases. The distinction between intractable, solvable but takes too long, and undecidable, no algorithm can solve it at all, is something the exam tests directly, and heuristics relate to both, but differently. What the exam will ask you for multiple choice questions. You'll often see a scenario describing a problem with exponential growth and possible solutions, and you'll be asked why a heuristic is appropriate. The answer is always tied to the trade-off. Exact solutions are not feasible in reasonable time, so a heuristic provides an approximate solution efficiently. You'll also see questions asking you to identify what a heuristic does not guarantee. Remember, it does not guarantee an optimal or correct solution. For free response questions, if you're asked to describe or justify a heuristic approach, you need to include 3 things: what the problem is, why an exact solution is impractical, and what the heuristic gives you in return, a good enough solution in reasonable time. Saying something uses a heuristic without explaining the trade-off will cost you points. Never confuse a heuristic with an algorithm that simply has some random element, and never say a heuristic is wrong. Imperfect and wrong are not the same thing. A solution 2% below optimal is still genuinely useful. With heuristics firmly in your toolkit, you're ready to zoom out and think about the big picture of what problems computers can and cannot solve. A conversation that leads us directly into the fascinating territory of undecidable problems and the limits of computation itself. 3.26 Reading and Writing Pseudocode, College Board Exam Reference Language. The universal language of the exam. Imagine you and a friend are trying to share a recipe, but one of you speaks Italian and the other speaks Mandarin. You'd probably end up drawing pictures or writing something simplified that both of you can understand. That's exactly what pseudocode is: a simplified, language-neutral way of writing out the logic of a program. And for the AP Computer Science Principles exam, College Board has created their own specific flavor of pseudocode that you absolutely must know cold. Think of it as the official language of the AP exam room. Every multiple-choice question involving code and every free response question where you write or trace code will use this exact notation. Get comfortable with it now, and you'll feel like you have a cheat sheet the entire test. The building blocks, variables, and assignment. Let's start with the most fundamental operation in any program: storing a value. In College Board's pseudocode, you assign a value to a variable using a left-pointing arrow, written as, so if you see x5, that means you're storing the value 5 into a variable called x. This is not the same as saying x equals 5 in a mathematical sense. It's a command, an instruction. You're telling the computer to take the value on the right and place it into the box on the left. This direction matters enormously on the exam. Here's a classic MCQ trap. You'll see something like x3, then yx, then x7, and you'll be asked what y equals. Many students panic and say 7. Because x changed. But E was assigned the value of x at the moment that second line executed, which was 3. After that, E doesn't care what happens to x. Variables don't hold relationships. They hold values captured at a specific moment in time. Arithmetic and expressions. For arithmetic, College Board uses the standard operators you'd expect: plus for addition, modo for subtraction, for multiplication, for division, and mod for modulo, the remainder after division. That last one is critical. The expression 17 mod 5 evaluates to 2, because 17 divided by 5 is 3 with a remainder of 2. You'll see mod used constantly in exam questions to check whether a number is even or odd, whether something divides evenly, or to wrap values around a range. If x mod 2 equals 0, x is even, Burn that into your memory. Conditionals, making decisions. Now let's talk about how programs make decisions, because this is where AP exam questions love to get tricky. College Board uses an if-else structure that looks like this. If, condition, followed by the block of code to run inside curly braces, and optionally else followed by its own block. The condition uses comparison operators like equals for not equal, and a less than or equaled, and then equal, less than or equal, and equal, and it's okay. What? Logical operators include and, or, and not. Here's where many students stumble. When you have a nested or chained conditional, the computer evaluates from top to bottom and stops at the first true condition. If your F is true, the else never runs, even if its condition would also be true. Picture a series of bouncers at a nightclub. As soon as one bouncer lets you in, you don't talk to the rest. The common wrong answer trap on MCQs is picking an answer that assumes multiple branches can execute. They cannot. Only one branch executes per run through a conditional. Iteration, loops, and repetition. This is the section where the exam really tests your ability to trace through code carefully. College Board gives you two loop structures. The first is repeat n times, which executes the block exactly n times. No conditions, no variations, just count and repeat. The second is repeat until condition, which keeps looping until the condition becomes true. Notice it says until, not while. This is a critical distinction. The loop continues as long as the condition is false and stops when it becomes true. If you're used to thinking in terms of while loops, you need to flip your mental model. The boundary condition trap here is common. What happens if the condition is already true before the loop starts? In College Board's repeat until, the loop body executes at least once before the condition is checked. It's what programmers call a do-while structure. So if the condition is true from the start, the body still runs one time. Many MCQ wrong answers hinge on students assuming the loop never runs in this scenario. Lists, storing collections of data. College Board pseudocode also includes list operations, and these connect directly to Unit 2's data concepts. A list is defined with bracket notation, like my list 10, 20, 30. Here's the crucial detail. College Board lists are BA1 indexed, meaning the first element is at position 1, not 0. If you've ever programmed in Python or JavaScript, this will feel wrong, but on this exam, my list 1 gives you 10. Forgetting this is one of the most common sources of off by 1 errors on the exam. You can access elements with mylist_i, find the length with length mylist, add an item to the end with append mylist value, insert at a position with insert mylist_i value, and remove with removed mylist_i. You'll often see these combined with loops. Iterating through a list from index 1 to length mylist is a pattern you should recognize instantly. Procedures and parameters. Procedures in College Board pseudocode are defined with prosquirtier name parameters and called simply by using the procedure's name with arguments. If the procedure returns a value, it uses return. Understanding how values pass into and out of procedures connects directly to Unit 3's broader discussion of abstraction. A procedure is a named, reusable abstraction of a process. On FRQ questions, you may be asked to write a procedure or trace through one, and the rubric will specifically check whether you're correctly handling the parameters and return value. The display statement and putting it all together. Finally, display expression outputs a value to the screen. This seems simple, but watch for it in tracing questions where you need to identify exactly what gets printed and in what order, especially inside loops. When you approach any pseudocode question on the exam, develop a consistent habit, grab a pencil, write out a small variable tracking table, and trace through the code line by line. Don't try to hold multiple changing values in your head. The students who lose points on pseudocode questions almost always do so because they skipped the slow, careful trace and made an assumption. Slow down, trust the process, and let the notation do the work for you. Understanding this pseudocode deeply also prepares you for the develop section of the create performance task, where you'll need to clearly describe the logic of your own program, and the cleaner your pseudocode thinking, the clearer your written explanations will be. With your pseudocode toolkit now fully assembled, you're ready to apply all of these structures to one of the most powerful ideas in computer science, the concept of algorithms themselves, including how we measure their efficiency and evaluate their correctness. 3.27 Input and output, user input, display print operations. Let's talk about something that is at the very heart of every program you've ever used, input and output. Think about the last time you used Google Maps. You typed in a destination, that's input. The app showed you turn-by-turn directions on your screen, that's output. Every single program, no matter how simple or sophisticated, follows this same fundamental loop. It receives information from the outside world, does something with it, and then communicates results back. Understanding this loop and how the AP exam tests it is exactly what we're doing right now. What the College Board means by input and output. The College Board defines input as data sent to a computer for processing. That input can come from a user typing on a keyboard, clicking a mouse, uploading a file, touching a screen, or even from sensors like a microphone or camera. Output is the result that a program displays or sends back: text on a screen, a sound, a printed document, or data sent to another program. On the AP exam, when you see the term user input, think of it as any value that comes from outside the program itself and influences how the program runs. That distinction, data coming in versus results going out, is something the exam will probe in subtle ways. In the AP pseudocode that College Board uses throughout the exam, user input is handled with the IMITMP statement, and display output is handled with displail. So if you see something like X input, that means the program is pausing, waiting for a user to supply a value, and then storing that value in the variable X. And when you see display of X, the program is sending the current value of X out to the screen for the user to read. These two operations are your primary tools for making a program interactive, and you will absolutely see them woven into multi-step pseudocode problems on the multiple choice section. Why input makes programs dynamic. Here's an analogy that makes this click. Imagine a recipe that always makes exactly 12 cookies, same ingredients, same proportions every time. That's a program with no input. It's static and inflexible. Now imagine a recipe app where you type in how many people you're serving and the app scales every ingredient automatically. That's input at work. The program's behavior changes depending on what you give it, and that's incredibly powerful. This is why the AP exam connects input directly to the concept of variables from earlier in Unit 3. A variable is just a named container for a value, and IPIT is often how that container gets filled at runtime, rather than having a fixed value baked in by the programmer. When a student asks, why not just hardcode the number? The answer is flexibility. Programs with input can serve millions of different users with millions of different needs without the programmer rewriting the code each time. The display statement and output precision. The display command in AP pseudocode outputs whatever expression or value you give it. You can display a variable, a string of text, or even a calculated expression. One important thing to know for the exam, display does not automatically move to a new line after printing in College Board pseudocode unless you're working in a context that specifies otherwise. This detail matters when you're tracing through code and predicting exactly what output looks like. If a question asks you to determine what gets printed on the screen step by step, read each display statement carefully and keep a running mental picture of the output as it accumulates. A common trap on multiple choice questions is misreading the order of operations between variable assignment and display. If you see a program that assigns a new value to a variable and then displays it, you'll see the new value. But if displail comes before the reassignment, you'll see the old value. This sounds obvious when stated plainly, but under time pressure, students frequently mix up the sequence and choose the wrong answer. Always trace through pseudocode line by line in order, updating your mental model of what each variable holds at each step. Edge cases and boundary conditions. The AP exam loves to test what happens when input is unexpected. What if a user is supposed to enter a positive number but enters 0? What if they enter a very large number that causes a calculation to overflow a reasonable range? These are boundary conditions, the edges of what a program is designed to handle. While AP-CSP doesn't require you to write error handling code at the level of AP-CSA, you are expected to understand conceptually that programs should account for the range of possible inputs and that poor input handling is a source of program errors. On free response questions, if you're asked to describe a limitation of a program, pointing out that the program doesn't validate its input, meaning it doesn't check whether the input is appropriate before using it, is a legitimate and often scoring answer. Connections to other units. Input and output don't live in isolation. They connect to virtually everything else in this course. In Unit 2, when you studied data and abstraction, input was how raw data entered a system. In Unit 5, when you study the impact of computing, you'll think about what kinds of input are collected from users and whether that raises privacy concerns, because every time a program takes input, it potentially stores personal data. The connection to algorithms in Unit 3 is direct. The algorithm processes the input and produces the output, and the quality of the algorithm determines whether that output is correct and useful. There's also a connection to program documentation and testing. When you design a program, thinking carefully about what inputs it will receive and what outputs it should produce is actually the starting point for writing good code and for designing good test cases. If your program is supposed to convert Celsius to Fahrenheit, the input is a Celsius temperature and the output is the Fahrenheit equivalent. And testing means checking that a known input produces a correct known output. The big picture. Here's the mental model you want to carry into the exam. Every program is, at its core, a transformation machine. Input goes in one side, the algorithm works its magic in the middle, and output comes out the other side. The input and dispel statements in AP pseudocode are the formal mechanisms for those entry and exit points, and understanding exactly when they execute and what values they carry at that moment is the skill the exam is testing. Get comfortable tracing code step by step, and you'll rarely be fooled. With input and output firmly in hand, You're ready to take the next step, because once a program can receive information and display results, the real question becomes, how do we make programs decide what to do with that information? That brings us to the fascinating world of conditionals and Boolean logic, where programs start making choices. 3.28. Managing complexity with procedural abstraction. What is procedural abstraction, and why should you care? Let's start with a story. Imagine you're making a cup of coffee every single morning. You don't think about every micro step. You don't consciously tell yourself, move hand toward cabinet, apply 3 newtons of force to handle, pull toward body at 45 degrees. You just think, make coffee. That single mental shortcut, bundling up a whole complex sequence of steps under one label, is exactly what procedural abstraction does in programming. It lets you take a complicated set of instructions, wrap them up, give them a name, and then use that name whenever you need the whole process. In AP Computer Science Principles, College Board calls this organizing your code into procedures, sometimes called functions or methods in other languages, and it is one of the most powerful ideas in all of computer science. The College Board definition you need to know cold. Procedural abstraction is the practice of defining and using procedures to manage the complexity of a program. A procedure is a named block of code that can be called or invoked by name whenever you need it. The key insight is that when you call a procedure, you don't need to know how it works inside. You only need to know what it does and what inputs it needs. That separation of what it does from how it does it is the soul of abstraction. Parameters, arguments, and the power of generalization. Here is where a lot of students get tangled up, so let's untangle it carefully. A parameter is the variable listed in the procedure's definition. It's a placeholder, a blank, waiting to be filled in. An argument is the actual value you pass in when you call the procedure. Think of a procedure like a recipe card. The recipe says, add X cups of sugar. That X is the parameter. When you actually bake the cake and decide to add 2 cups, 2 is the argument. Why does this matter so much? Because parameters are what transform a procedure from a single-use tool into a general-purpose machine. If you write a procedure called calculate area that takes a length and a width as parameters, you can call that procedure for any rectangle in your program without rewriting the logic each time. Without parameters, you would need a separate procedure for every single rectangle. With parameters, one procedure handles all of them. This is generalization, and it is a core exam concept. College Board loves asking questions about how parameterizing a procedure increases its usefulness and reduces code duplication. The 2 giant benefits, reusability and readability. The AP exam tests 2 major benefits of procedural abstraction over and over, and you need to articulate both clearly, especially on free response questions. First is encode reusability. Once you have defined a procedure, you can call it as many times as you want anywhere in your program without copy-pasting the same lines of logic repeatedly. This is critical because duplicated code is a programmer's nightmare. If you need to fix a bug or make a change, you would have to track down every single copy. With a procedure, you fix it once in one place, and every call to that procedure automatically benefits from the fix. The FRQ rubric will specifically look for this idea when it asks you to justify using a procedure. Second is readability and maintainability. When your main program says, display welcome message, user input, and process results, a reader can understand the flow of the program at a high level without getting buried in details. Each procedure name acts like a chapter heading in a book. It tells you what happens without making you read every sentence. College Board phrase to remember. Procedures allow programmers to manage program complexity by breaking a problem into smaller, more manageable subproblems. Common MCQ traps to watch out for. The exam is notorious for a few specific traps in this topic area. The first trap involves scope. Variables defined inside a procedure are local to that procedure. They do not exist outside of it. If a question shows a variable count created inside a procedure and then asks what happens when the main program tries to access count, the answer is that it is not accessible there. Do not confuse variables passed as arguments with variables that persist after the procedure ends. The second trap involves what a procedure returns versus what it displays. A procedure that uses a return statement sends a value back to wherever it was called. That value can then be stored or used in further computation. A procedure that simply displays something on screen does not return anything useful to the calling code. Exam questions will sometimes show a procedure that displays a result, and then ask about code that tries to store the result of calling that procedure. If the procedure doesn't return anything, there's nothing to store. Read every procedure carefully for return statements. The third trap is assuming that abstraction always means the code is shorter. Sometimes a well-abstracted program actually has more total lines because of the procedure definitions, but it is still easier to read, debug, and reuse. Complexity management is about cognitive simplicity, not necessarily fewer characters on a page. Connecting to the bigger picture. Procedural abstraction does not live in isolation on the AP exam. It connects to several other units you need to master in Unit 2. When you studied how the internet and systems are built in layers, each layer is a form of abstraction. Lower layers do the hard work, while higher layers simply make calls to them without knowing the details. In Unit 4, when you analyze algorithms for efficiency, Well-named procedures make it far easier to reason about what a program is doing step by step. In the Explore Performance task, Create Task on older exams, you are explicitly required to include a student-written procedure with a parameter that affects the functionality of the program. Knowing this section cold directly earns you scoring points. The rubric specifically asks whether your procedure contributes to the program's functionality and whether it uses a parameter meaningfully, not just cosmetically. Also connect this to libraries and APIs, which are the ultimate expression of procedural abstraction at scale. When you call a function from a library, say a sorting function, you are trusting that someone else wrote and tested that procedure, and you benefit from it without needing to understand every line inside. This is the same principle, just at a grander scale. The one-sentence exam mantra. If you walk away with one idea locked into your memory for test day, let it be this: a well-designed procedure hides complexity, accepts general inputs through parameters, and can be reused anywhere in a program, and that combination is what makes large, sophisticated programs possible to build and understand. With the power of procedures now in your toolkit, you're ready to zoom out and look at how programmers organize entire collections of related procedures into something even more powerful, which brings us right to the heart of how modern software is structured and maintained at scale. 3.29 Identifying and correcting errors, syntax, logic, runtime, and overflow errors. Imagine you're baking a cake and you follow the recipe perfectly, or so you think. But when you pull it out of the oven, something is clearly wrong. Maybe you misread teaspoon as tablespoon of salt. Maybe you mixed the ingredients in the wrong order. Maybe the oven temperature was too high and the batter overflowed the pan. Each of those mistakes is a different kind of error, and each one requires a different fix. That's exactly how programming errors work, and the AP exam expects you to not only recognize each type, but to diagnose them with precision and explain how to correct them. Let's break down every category you need to know. Syntax errors. A syntax error is like a grammatical mistake in a language. You broke the rules of how the language itself is written. In a natural spoken language, if you say "I good to store the," people might still understand you, but a computer has zero tolerance for this kind of thing. The program simply refuses to run. Think of a syntax error as trying to start your car with a key that's been cut the wrong way. It won't even turn in the ignition. In the AP pseudocode that College Board uses on the exam, syntax errors include things like forgetting to close a parenthesis, using the wrong assignment operator, or misspelling a keyword. What's critical to understand for the exam is that a syntax error is caught before the program runs, at what we call compile time or interpretation time. The program never even gets off the ground. On the multiple choice section, if you see a question asking why a program will not run at all, syntax error is your immediate go-to answer. Logic errors. Logic errors are the sneaky ones, the truly dangerous bugs, because the program does run, and it runs without crashing, but it produces the wrong answer. This is the equivalent to following your cake recipe perfectly but accidentally grabbing vanilla extract when you meant to grab almond extract. The cake comes out of the oven looking fine. You slice it, take a bite, and think, wait, that's not right. A classic logic error example. Suppose you're writing a program to find the average of a list of numbers, and you write total/10 instead of total/count. Hard-coding the wrong divisor. For a list with 10 numbers, it works. For any other size list, it quietly gives you a wrong answer. No error message, no crash, just a lie dressed up as a result. On the AP exam, logic errors are the trickiest to spot in code reading questions because everything looks legal. Always trace through the code step by step with a specific example value to catch these. Ask yourself, does the output match what the problem description says it should produce? Common traps on MCQs involve off-by-one errors, where a loop runs one time too many or one time too few, and incorrect conditional logic like using instead of is greater than or. These are almost guaranteed to appear. If a question shows a loop that should process 10 items but only processes 9, that's a logic error, not a syntax error, and definitely not a runtime error. Runtime errors. A runtime error is one that only shows up while the program is actually executing, like a bridge that looks structurally sound until a truck drives across it and it collapses. The program starts running just fine, but then something goes wrong mid-execution and the program crashes or terminates abnormally. The most iconic example is dividing by zero. Your code might look perfectly legal. Divide a number by a variable x. But the moment x holds the value 0 at runtime, the program throws an error and halts. Another classic runtime error is trying to access an index that doesn't exist in a list. If your list has 5 elements and you ask for element number 10, that's a runtime error called an indexed out of bounds error. Notice the key distinction here. The program had to actually run and reach that line for the error to occur. This is why boundary conditions matter so much. On the AP exam, look for situations where a variable might unexpectedly hold an extreme value, 0, a negative number, an empty list, and ask whether the code handles that case gracefully. If it doesn't, you're looking at a potential runtime error. Overflow errors deserve special attention because students often underestimate them. Computers store numbers using a fixed number of bits. This means there's a maximum value any given integer type can hold. If a calculation produces a result that exceeds that maximum, the number wraps around or produces a completely incorrect value, and the program may not even know it happened. Picture a car's odometer that only goes up to 999,999 miles. The moment it hits 1 million, it rolls back to 00. That's overflow. On the AP exam, overflow is often discussed in the context of why computers can't represent every possible number exactly, and why careful programmers must account for this limitation. A common MCQ scenario gives you a calculation involving very large numbers and asks which type of error could occur. Overflow is the answer when the result exceeds the storage capacity of the variable's data type. This also connects directly to Unit 2's coverage of binary representation and the limits of how data is stored. Keep that connection sharp in your mind. Identifying versus correcting. What the exam actually asks. The AP exam doesn't just want you to name the error type. It often asks you to correct the error or explain what change would produce the intended behavior. For syntax errors, the fix is usually straightforward: repair the broken syntax. For logic errors, you need to rethink the algorithm itself, maybe change a conditional, adjust a loop boundary, or fix a formula. For runtime errors, the correction often involves adding a guard condition, like checking that a divisor isn't 0 before dividing, or verifying that a list index is valid before accessing it. For overflow, the fix typically involves using a larger data type or redesigning the algorithm to avoid producing excessively large intermediate values. A powerful exam strategy. Whenever you're given a code snippet with an error, trace through it manually using a simple concrete input. Write down the value of each variable at each step. This turns abstract code into a story you can follow, and errors reveal themselves almost immediately. The AP exam frequently uses this technique in free response questions, rewarding students who show their trace clearly and label their reasoning with precise terminology. This is a logic error because the program runs but produces incorrect output. These 4 error types also connect forward to topics like algorithm design and testing in later units, because understanding errors is fundamentally about understanding how to write programs that behave correctly under all conditions, including the edge cases that try to break them. Next, we'll look at how those same ideas power the process of searching and sorting, where the logic of your algorithm is everything. 3.3. Create performance task, program design, development, and documentation. Let's talk about something that can feel both exciting and a little nerve-wracking: the Create Performance Task, or CPT. This is your chance to actually build something and have it count towards your AP score. No multiple choice bubbles, no guessing. But that also means you need to understand exactly what College Board is looking for, because the rubric is very specific. Think of this section as your blueprint before construction begins. We're going to walk through what the task actually requires, how to design and develop your program the right way, and critically, how to document it so that a scorer who has never met you can see your thinking clearly. What the Create Performance Task actually is? The CPT is a significant piece of your AP score. You spend roughly 12 hours of class time, plus whatever personal time you invest, building a program that does something meaningful to you. Then you submit a video of it running, a written response that explains your design choices and portions of your actual code. The College Board scores your submission using a rubric with specific rows, each worth 1 point for a total of 6 points. Every single row is pass or fail. You either demonstrate the required element completely or you don't. There's no partial credit within a row, which is why precision in your documentation matters just as much as the quality of your code. Program design, starting with purpose. Here's an analogy that might help. Imagine you're an architect hired to design a building. Before you ever pick up a pencil, you ask, what does this building need to do? The same logic applies to your CPT program. You start with a purpose. What problem does your program solve, or what experience does it create? College Board wants you to demonstrate that your program was intentionally designed, not accidentally assembled. When you write your written response, you'll be asked to describe the overall purpose of your program and what the user can do with it. Keep that purpose statement crisp and concrete. My program helps users track daily water intake and notifies them when they're behind. Their goal is far stronger than my program is about water and health. One of the most common traps students fall into is writing a purpose statement that describes the program's features instead of its goal. Features are what the program does. Purpose is why it exists. Make sure your response makes that distinction clear. The complexity requirements, lists, and procedures. 2 rows of the rubric are so important. They deserve their own spotlight. The list and the procedure with a parameter and algorithm. Think of these as the 2 structural pillars College Board is checking your code for. For the list requirement, you need to use a list or another collection type in a meaningful way. That means the data stored in the list must actually influence the program's behavior in some demonstrable way. If you create a list and then never do anything with it, it doesn't count. The key question to ask yourself is, would my program work just as well without this list? If the answer is yes, you need to redesign how the list is used. The list needs to be managing complexity, a term College Board uses explicitly. A list manages complexity when using it allows your program to handle a variable or unknown number of items in a clean, scalable way, versus writing out a separate variable for every possible case. For the procedure requirement, you need a student-defined procedure that takes at least one parameter, contains an algorithm that includes sequencing, selection, and iteration, and is actually called somewhere in your program. Notice all three conditions must be true simultaneously. A lot of students write a great procedure, but forget to call it instant loss of that point. Others write a procedure that's called but has no meaningful selection inside, no conditional logic, and they lose that point too. When you sit down to write your procedure, mentally check off, does it have a parameter that actually affects what it does? Does it have an if statement or equivalent conditional? Does it have a loop? Is it called elsewhere in my code? Documentation and the written response. Your written response is where you translate your code into human language. One thing students consistently underestimate is that the scorer is not running your code. They're reading your description. If your explanation is vague or incomplete, no assumption will be made in your favor. You have to earn every point explicitly. When describing your list, you need to explain what the list represents in your program and then describe a specific algorithm that includes using the list. Walk through the steps as if you're explaining it to someone who has never seen code before. When describing your procedure, you need to explain what it does, how the parameter affects its behavior, and what would happen with two different calls using different parameter values. That last part, showing two different inputs and their outputs, is something many students skip because they think it's implied. It's not implied. Write it out. Video submission. Your video is short, 1 minute maximum, and it needs to show your program running, with the input and output visible. You do not need to narrate or appear in the video. What College Board needs to see is that your program actually functions. A common mistake is showing a video where a key feature, like the list-based functionality, never appears on screen. Plan your video deliberately. Walk through the path that showcases as many rubric elements as possible in 60 seconds. Connections to the broader course. The CPT pulls together nearly everything from Unit 3 and beyond. Your list usage connects to the data abstraction concepts from earlier in the unit. Your procedure connects to the abstraction and modularity discussions. The algorithm inside your procedure, with its sequencing, selection, and iteration, mirrors the exact algorithmic thinking you've practiced reading and tracing in pseudocode exercises. Even the concept of program purpose connects to the big ideas of impact and innovation from Unit 1. When College Board says this task is integrated, they mean it. You're not doing something separate from the course, you're showing that all of it lives together in one working piece of software. Keeping your own work yours. One boundary condition that students sometimes overlook. The code you submit must be your own. You can collaborate during development, but the code you select for your written response, the list segment and the procedure segment, must be code you personally wrote. If your partner wrote the core procedure, you cannot submit it as yours, even if you understand it deeply. Choosing which segments to highlight is a strategic decision, so pick code that you can explain thoroughly because you built it yourself. The Create Performance task is genuinely one of the most rewarding parts of this course. It's the moment where abstract concepts become something real that runs on a screen. Up next, we'll transition from building programs to thinking critically about how programs affect the world around us, diving into the global impact and ethical implications of computing.